concept of nothingness at first glance seems simple enough. Yet, as we begin to examine it more deeply, we quickly realize how complicated and perplexing it truly is. Our universe, as we understand it, began from what appears to be nothing. Yet, what does that truly mean? Is there a state where absolute nothingness exists? Or is it possible that nothing itself has a hidden form of existence, a background from which something could emerge? And where, in the grand scheme of things, did this nothingness even come from? Long before modern science began to shed light on the universe's mysteries, ancient thinkers were already grappling with these questions. Some of the earliest and most influential philosophers asked the fundamental inquiries that still resonate today. What does it mean to exist? Can something truly be said to exist if there is such a thing as absolute nothing? Among these ancient philosophers, one of the boldest and most intriguing was Parmenides, an influential thinker from ancient Greece. Parmenides famously asserted that nothing could ever truly exist. To him, the very concept of nothing was self-contradictory. How could something be considered truly absent if it were, in fact, able to be thought about or described? To him, the idea of nothingness was logically impossible. According to Parmenides, existence was eternal, without beginning or end. The universe, in his view, was not created, but simply always was. For him, if there had ever been a time when there was truly nothing, no matter, no energy, no existence, then how could anything ever come into being? His perspective forces us to confront some deep and uncomfortable questions. If nothingness is impossible, does it mean that the universe has existed in some form for eternity? Was it never created but merely always there? However, Parmenides was not the only philosopher to ponder these profound questions. His ideas were met with dissent even in his own time. Aristotle, another towering figure in ancient philosophy, offered a different perspective. For Aristotle, nothingness wasn't a contradiction, but rather a potential, an empty slate upon which something could emerge. Imagine, if you will, an artist's canvas. Before the brush touches the surface, it appears empty, but in reality, it holds endless possibilities. Similarly, Aristotle argued that even in what appeared to be empty space, there was an underlying potential for creation. Though space may seem devoid of substance, it was not a true void. Instead, it was brimming with potential, ready to bring forth new things. For centuries, these two contrasting views, one that nothingness is impossible and the other that nothingness is a fertile ground for creation, continued to shape the philosophical debates. As thinkers pondered the nature of existence and nothingness, they inevitably found themselves considering the nature of the universe itself. If the universe could emerge from nothing, what sort of nothing was that? These questions pushed the boundaries of human thought and forced philosophers to reconsider their most basic assumptions about the reality we inhabit. Fast forward to the modern era, and the questions about nothingness took on an entirely new dimension. One of the most influential philosophers of the Enlightenment, Immanuel Kant, questioned whether nothingness, true, absolute nothing, was something that the human mind could even comprehend. Kant suggested that the concept of nothingness was beyond our capacity to truly understand. Our existence, after all, is founded upon a world that is full of tangible things, matter, space, time, things we can feel, measure, and observe. But Kant argued that true nothingness, the absolute absence of everything, is so foreign to our experience that it lies outside the limits of human cognition. Could it be that nothingness, in its purest form, simply doesn't exist, or that our minds are simply incapable of grasping its true nature? This leads us to a crucial and fundamental question. If nothingness doesn't exist in the way we think it does, then could it be the very source of everything we see around us? Could it be that nothingness is not truly an absence, but a hidden spark, the origin of all creation? This paradox has intrigued some of the greatest minds throughout history, all of whom have wrestled with one of the most enduring mysteries, the birth of the universe itself. As science continued to evolve, so too did our understanding of nothingness. While ancient philosophers engaged in abstract debates, science quietly moved forward with a different approach. Using tools like mathematics and experimentation, scientists began to uncover the true nature of the universe. And in the 20th century, a groundbreaking discovery forever changed our understanding of nothingness. The work of Albert Einstein reshaped how we view the cosmos, showing that space and time were not separate entities but intricately linked, forming a flexible dynamic fabric known as space-time. This revelation was nothing short of revolutionary. It meant that space wasn't a static void, a mere backdrop where events took place. Instead, space itself was active and responsive, affected by the presence of mass and energy. This insight turned the idea of nothingness on its head. Space was no longer an empty, lifeless vacuum. It was a dynamic medium that shaped the events of the universe. But the real transformation in our understanding of nothingness came with the advent of quantum mechanics. Quantum physics deals with the smallest building blocks of the universe, the particles that are too tiny to be seen with the naked eye. And it revealed something truly strange. Even in the emptiest regions of space, regions that seemed devoid of matter, energy, and light, something was still happening. It was subtle, almost imperceptible, but it was there nonetheless. This phenomenon is known as quantum fluctuations, tiny bursts of energy that appear and vanish in an instant. In a perfect vacuum, a space completely empty of matter and light, one might expect complete stillness. But on the smallest of scales, the universe is far from still. These quantum fluctuations are brief, fleeting, and on a scale so small that they cannot be seen directly. Yet they are real, measurable phenomena. Even in what appears to be empty space, invisible fields of energy are constantly fluctuating, creating tiny particles that exist for only the briefest of moments before disappearing again. These particles are called virtual particles, and even though their existence is ephemeral, they leave behind detectable traces. This discovery introduced a profound and unexpected idea. The vacuum of space, what we once thought of as true nothingness, is actually alive with energy, constantly fluctuating and teeming with potential. This brings us to a tantalizing possibility. Could this quantum activity be the key to the origin of everything? Could the universe itself have emerged from a quantum fluctuation? In this view, the universe could have originated from a minuscule burst of energy that sprang into existence from what we once considered to be absolute nothing. This idea, if true, would radically alter our understanding of the cosmos. The universe might not have been created from some external force or divine intervention. Instead, it could have come into being through the natural, if extraordinary, laws of quantum mechanics. The concept of a universe arising from nothing is both awe-inspiring and perplexing. It suggests that the universe could have emerged from what seemed like an empty vacuum, filled only with the potential for creation. This theory is not just speculation. Some of the brightest minds in modern physics, including Stephen Hawking and Lawrence Krauss, have explored this very possibility. According to Krauss, quantum fluctuations, the unpredictable movements of particles in the vacuum, could give rise to entire universes. In his book, A Universe from Nothing, Krauss argued that the entire universe could have emerged from a fluctuation, much like how virtual particles briefly appear in the empty space of a quantum vacuum. This line of thinking challenges our deepest intuitions about creation and existence. If the universe could come from nothing, then what does nothing really mean? Is it simply a void awaiting the right conditions to give rise to existence? Or is it something much deeper, a hidden wellspring of energy that could bring forth everything we know? These are the questions that continue to occupy the minds of scientists and philosophers alike, pushing the limits of human understanding and offering us a glimpse into the very heart of reality itself. However, this concept of nothing is far more complex and mind-boggling than it might first appear. Throughout the history of philosophy, thinkers have long debated the notion of potential. This idea suggests that even in what seems like nothingness, there is a hidden energy, an untapped possibility, just waiting for the right conditions to emerge. It's as though nothing is not truly empty at all, but is instead a vast, uncharted space brimming with infinite potential. To think of nothing as empty might be to misunderstand its true nature entirely. In the realm of science, this idea takes on an even more astonishing form, particularly through the lens of quantum physics. We have now come to understand that even the most seemingly void-like space is far from empty. Instead, it's alive with tiny, energetic fluctuations. These fluctuations are so powerful, in fact, that they hold the potential to give birth to entire universes. Imagine that. What we once thought of as a barren, empty void is in reality teeming with the kind of energy capable of creating something as grand and intricate as an entirely new universe. While science and philosophy have provided us with these awe-inspiring insights, the truth remains that we may never fully comprehend the true nature of nothing. Nevertheless, what is crystal clear is that this mystery is far from trivial. It's one of the most profound puzzles humanity has ever encountered. The more we contemplate it, the more we come to realize that the origin of everything, the story of how everything came to be, is just as mind-blowing and unfathomable as the universe itself. This concept of nothingness has intrigued thinkers for centuries. Ancient philosophers, from the Greeks to the early Eastern thinkers, grappled with its meaning. Fast forward to today, and modern scientists are uncovering even more mind-bending truths. From the quiet reflections of those ancient minds to the cutting-edge discoveries unfolding in laboratories today, the idea of nothing continues to captivate and hold us in awe. As we stand beneath the endless night sky filled with billions of stars and swirling galaxies, we are reminded that the most extraordinary story of all may very well be the one that begins with nothing. In the vastness of space, when we gaze upon the brilliance of stars and the majestic spirals of galaxies, it is humbling to think that these awe-inspiring wonders may have arisen from what once seemed to be absolute emptiness. Could it be that the universe we know and everything in it, our very existence, emerged from nothing at all? The idea that something so magnificent could arise from a state of complete nothingness is what makes our universe and our place within it so endlessly fascinating and mysterious. Picture this for a moment. Everything you see around you, the entire universe with its countless galaxies, stars, planets, and even the tiniest specks of dust, was once crammed into a space so small that it was smaller than an atom. It sounds nearly impossible to believe, right? Yet this is not the stuff of science fiction. It's the very foundation of one of the most astounding theories in all of science, the Big Bang Theory. This idea serves as the cornerstone for how our entire universe came into being, and it's a story that's as extraordinary as the universe itself. The Big Bang Theory is the most widely accepted explanation for the origin of the universe. According to this theory, everything we know, everything from the stars lighting up the sky to the atoms that make up every material object around us, emerged from a single, incredibly tiny, infinitely dense point. This point was so small that it defies comprehension. Yet, within this minuscule, concentrated singularity existed all the energy, matter, and potential that would eventually give birth to the vast universe we now experience. From that singular point, everything that exists today, our universe in all its beauty, complexity, and expansion, came into being. But how did this all happen? What exactly was this bang, and how did it give rise to everything we know? To answer this, we must embark on a remarkable journey back in time, almost 14 billion years, to the very moment when time and space themselves were born. Before the Big Bang, there was no universe as we understand it today. Asking what came before the Big Bang is like asking for directions to a place north of the North Pole. There was no before in the conventional sense. There was no time, no space, no matter. Everything we know and experience was packed into an incredibly hot and dense point, a concept known as a singularity. Picture this singularity, a point that contained all the energy, all the matter, and all the potential for the universe. Everything that would eventually become the galaxies, stars, and planets we see today was once contained within this unimaginably small and dense space. Trying to visualize this is almost impossible, but this singularity was the seed, the origin of everything that would follow. It was the birthplace of the universe. Then, around 13.8 billion years ago, something extraordinary occurred. For as long as time could be measured, for as long as time itself existed, there had been nothing. No universe, no stars, no galaxies. And then, in the blink of an eye, there was everything. This tiny, dense singularity exploded, not in the way an ordinary bomb goes off, but in a far more dramatic way. The Big Bang wasn't an explosion within space. Rather, it was the rapid and sudden expansion of space itself. In a fraction of a second, space expanded from being smaller than an atom to something billions of times larger, and the expansion didn't occur in a specific direction. Instead, space itself stretched out, carrying everything with it. The Big Bang, in essence, was the birth of time, space, and everything we know. But that was just the beginning. The real question is, what happened next? How did that initial burst of energy, the incredible explosion of space, transform into the galaxies, stars, planets, and all the other structures we see in the universe today? To understand this, we need to follow the timeline of events that unfolded after the Big Bang. In the earliest moments of the universe's existence, things began to cool down and take shape. Clouds of gas formed, stars ignited, and galaxies began to coalesce. Each galaxy was a massive collection of stars and other matter floating through the expanding universe. Over billions of years, these stars and galaxies continued to evolve, creating the vast and complex cosmos we observe today. The journey from that infinitesimally small hot point to the immense, sprawling universe we live in now is one of the most incredible stories of all time. To truly grasp how the universe evolved, we must break it down moment by moment, even to the tiniest fractions of a second. In the early universe, so much happened in what seemed like no time at all. And these moments, though brief, were crucial. Let's begin at the very beginning, at a time so early that it's hard to even imagine. During the Planck epoch, the universe was in a state unlike anything we can comprehend today. This was less than a trillionth of a second after the Big Bang, when the universe was incredibly tiny and unimaginably hot, hotter than anything we can fathom, a temperature over a quadrillion degrees. In this extreme environment, all four of the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were united into one single force. This concept is difficult for us to fully grasp because in our everyday experience, these forces work independently. But during the Planck epoch, they were unified. What does that mean? Essentially, everything we know about the laws of physics, the very science that governs our universe, was merged into a single force. But here's the catch. We don't fully understand what happened during this time. Our best scientific theories, such as Einstein's theory of general relativity and quantum mechanics, break down under the extreme conditions of the Planck epoch. It's as if we're trying to fit pieces of two completely different puzzles together, and they just don't match. What we do know, however, is that during this brief moment, the universe expanded at an incomprehensible speed. Imagine space itself stretching out at a rate far faster than anything we can even begin to conceive. The speed and scale of this expansion were so profound that they marked the beginning of everything we know. And it all started in what we can only describe as a moment of unfathomable potential, a moment when nothingness transformed into everything. At the moment of the Big Bang, the universe was an incredibly hot and dense place, so much so that not a single photon could break free. Everything was wrapped in a thick cosmic fog, a veil that hid all the processes taking place. At that time, the universe was far from the familiar cosmos we observe today. It was a hot, chaotic soup of particles, unable to emit light in any form. Looking back, it was impossible to see past this cosmic fog, which blocked us from directly observing those early moments. The universe at that stage was a furnace of unimaginable heat, where light could not travel freely. However, as the universe began to cool, though cool in this context is a relative term, considering it was still millions of times hotter than the sun's core, the conditions began to change. The first major shift came when gravity separated itself from the other three fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity, once unified with the others, began to act on its own. This marks the beginning of what is known as the Grand Unification Epoch, a pivotal moment in the early universe when gravity ceased to be one with the other forces. Meanwhile, the remaining forces, electromagnetism, the strong nuclear force, and the weak nuclear force, continued to act together, but gravity had now begun its separation. The universe, in its early moments, was dynamic and ever-changing. The expansion of the universe in the moments after the Big Bang became a crucial event in the history of existence itself. But then something unexpected happened. The universe's expansion, for a brief moment, slowed down slightly. This might sound minor, but it was actually just the precursor to something far more profound. The real change was yet to come. Around 1/septillionth of a second after the Big Bang, the universe underwent an extraordinary event known as inflation. This was not just a slight shift. It was an incredibly rapid, explosive expansion that stretched space itself at a rate unimaginable to the human mind. Faster than the speed of light, in fact. This mind-boggling speed caused the universe to grow exponentially, expanding from the size of an atom to a size billions of times larger in a fraction of a second. Picture something so vast and complex growing almost instantaneously. It's nearly impossible to comprehend. Why did this rapid inflation happen? The truth is, scientists don't yet have a clear answer. The mystery still lingers, though one leading theory points to a special type of energy called the inflaton field. This energy was responsible for stretching space itself beyond the speed of light. As the universe expanded at this astonishing pace, it wasn't just the matter and energy that spread out. Space itself was expanding, creating room for the galaxies, stars, and planets that would eventually emerge. Following this explosive expansion, the universe began to cool, albeit still incredibly hot. As the temperature dropped, the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, began to separate further. Each force began to act independently, paving the way for matter to slowly form. This cooling allowed the next crucial step in the universe's evolution, the formation of subatomic particles. At this point, quarks and gluons, the fundamental building blocks of matter, were born. Quarks are the basic components of protons and neutrons, while gluons are the particles that hold quarks together via the strong nuclear force. The universe entered a chaotic period known as the quark epoch. It was a time of intense energy and constant collisions, with particles constantly interacting, breaking apart, and reforming. Despite the high temperatures, the particles couldn't yet bind together to form stable structures, but they were setting the stage for everything that would come. For a while, everything in the universe existed in a kind of frenzied, constant fluctuation. It was like a cosmic soup, where particles flickered in and out of existence at incredible speeds. However, as the universe continued to cool, the forces that held these particles together began to strengthen. Slowly, the subatomic particles began to stick together, marking the early steps toward the formation of matter as we know it. Around 10 seconds after the Big Bang, photons, tiny particles of light, played a vital role in shaping the universe's evolution. By this point, the universe was still filled with free electrons and protons, and these electrons were constantly interacting with the photons. This constant scattering prevented light from traveling freely, causing the universe to remain opaque, much like a thick fog. But then something extraordinary happened. Over the next few minutes, the first atomic nuclei began to form through a process called nucleosynthesis. Protons and neutrons combined to create the first nuclei of the lightest elements, hydrogen, helium, and a little bit of lithium. These elements, hydrogen and helium in particular, became the fundamental building blocks of matter. They would eventually form stars, galaxies, and all the structures that would come to populate the universe. Yet, it would take hundreds of thousands of years before the universe cooled enough for light to travel freely through space. This cooling led to a crucial turning point, the era of recombination, which occurred several 100,000 years after the Big Bang. By this time, the universe had cooled sufficiently for protons and electrons to combine into neutral atoms, primarily hydrogen. For the first time, the universe became transparent enough for light to travel freely. Prior to this, light had been trapped in a fog of hot, charged particles, constantly scattering and never traveling far. But now, the universe cleared up, and light could spread out across space unimpeded. This moment marked a pivotal shift, a moment of clarity in the universe's evolution, and left behind something of immense importance: the cosmic microwave background radiation, CMB. The CMB is often referred to as the afterglow of the Big Bang. It is the faint, residual heat left over from the early universe. Even today, billions of years later, the CMB is still detectable, providing scientists with a snapshot of the universe when it was just 380,000 years old. This glow is a direct remnant of the universe's infancy, offering valuable insight into what the cosmos looked like in its early moments. The CMB provides evidence of the hot, dense plasma that existed in the early universe, and its uniform distribution across the sky gives further weight to the idea that the universe began from a single, incredibly hot point. So how do we know all of this with such confidence? How can we be certain about the Big Bang Theory? The answer lies in the multitude of evidence that supports it. First, there is the cosmic microwave background radiation itself, discovered in 1965 by scientists Arno Penzias and Robert Wilson. The CMB is one of the strongest pieces of evidence, a direct remnant of the Big Bang, and it's uniform across the sky, confirming the theory of a hot, dense origin. Next, there is the phenomenon known as redshift. When we observe distant galaxies, the light coming from them is stretched toward the red end of the spectrum. This effect, known as redshift, occurs because the universe is expanding. As space itself stretches, it pulls on the light traveling through it, causing it to appear redder. This discovery, made by astronomer Edwin Hubble in the 1920s, showed that galaxies are moving away from us, and the farther they are, the faster they move. This is a key indication that the universe is expanding, and that it must have begun from a small, dense point. Finally, the abundance of light elements like hydrogen, helium, and lithium in the early universe provides another powerful piece of evidence. During the first few minutes of the universe's existence, nuclear fusion took place, creating the lightest elements in vast quantities. Today, the universe is still composed primarily of hydrogen and helium, with trace amounts of heavier elements. This matches predictions made by the Big Bang Theory, which holds that the universe went through a hot, dense phase where these elements were created. The Big Bang Theory tells a remarkable story of how the universe began, starting from a tiny, hot, dense point that exploded, giving birth to the cosmos as we know it today. From that explosion, particles began to form, eventually giving rise to stars, galaxies, and all the structures that populate the universe. But the story didn't stop there. The universe has continued to expand and evolve over billions of years. Even today, space itself continues to stretch, and this process is expected to continue for billions, perhaps trillions of years into the future. The universe remains a vast, ever-changing puzzle, and scientists are only beginning to understand how its pieces fit together. However, the Big Bang Theory does more than simply explain the birth of the universe. It also gives rise to even more profound questions that echo through the halls of scientific inquiry. While it has unraveled much about how the cosmos came into being, it simultaneously leaves us with a labyrinth of mysteries still to solve. With each new discovery, we take another step closer to comprehending the unfathomable forces that shaped not only the universe's beginnings, but potentially its future demise. The journey of understanding is far from over. From the minute particles formed in the first fractions of a second after the Big Bang, to the majestic galaxies that stretch across the observable universe today, the story of our cosmos is immense and still unfolding. The Big Bang Theory provides a window into this unfolding narrative, offering us a glimpse into the breathtaking saga of existence, beginning with an explosion of unimaginable magnitude and complexity. The theory is like opening the first chapter of an epic book with no end in sight, leaving us to wonder not only how everything started, but what comes next. It is a story that is still being written, one discovery at a time. As we attempt to uncover the origins of the universe, we inevitably face one of the greatest enigmas in modern science, the singularity. It is a point in time, if time itself can even apply, at the very heart of the Big Bang, where our understanding of physics falters. For years, scientists have posited that this singularity was the source of all things, space, time, matter, and energy, emerging in one explosive moment. But this notion leads to an even more profound question: what came before the Big Bang? In simple terms, a singularity is a point where the laws of physics as we know them cease to function. It is a place where matter becomes infinitely dense, and the gravitational forces are so intense that they warp space and time beyond recognition. In this realm of extreme conditions, even Einstein's celebrated theory of general relativity, which governs the behavior of large objects like planets and galaxies, breaks down. What does this mean for us? It means that our current understanding of the universe cannot even begin to explain what happens inside a singularity. The singularity at the birth of the universe is even more perplexing than those that exist within black holes. A black hole's singularity, for instance, is confined to a region inside a collapsing star. The Big Bang singularity, however, is not the remnant of a star's collapse. It is the very beginning of everything. Space, time, and the entire cosmos squeezed into a point of infinite density. Then, in an instant, it exploded, creating the universe we know. But this is where things get even more mysterious. If the Big Bang created both space and time, what existed before time itself began? To ask what came before the Big Bang is to assume that time existed before the universe began. However, according to Einstein's theory of relativity, space and time are part of the same fabric, called space-time. If the Big Bang gave birth to space-time, then time itself did not exist before the singularity. The question of before becomes nearly meaningless in this context. Yet, some physicists believe there is more to the story than what we can currently grasp. Theoretical models offer a variety of possibilities. One such theory suggests that the universe does not have a singular origin, but instead follows an infinite cycle of expansion and collapse. In this model, the universe expands, reaches a peak, then contracts back into a singularity, only to explode again in another Big Bang. This endless cycle of creation and destruction could imply that something always existed before our current universe, possibly in a different form. Another intriguing theory draws from the strange world of quantum mechanics, the science that governs subatomic particles. Quantum physics suggests that particles can spontaneously pop in and out of existence, even in empty space. Some physicists propose that the entire universe may have emerged from a quantum fluctuation in an empty void, implying that before the Big Bang, there was nothing. But also, there was everything, a vast emptiness teeming with unpredictable quantum activity. Perhaps, some have speculated, our universe is just one of many. In this view, the cosmos we inhabit is part of an endless multiverse, with universes constantly being created in a boundless, ever-expanding sea. If this is true, then something always existed before our universe, not in the way we might imagine, but as another universe, or an entirely different state of existence. The 1970s saw major breakthroughs in our understanding of singularities, thanks to the work of two of the most brilliant minds in physics, Stephen Hawking and Roger Penrose. These two scientists managed to merge Einstein's theory of general relativity with the strange and unpredictable laws of quantum mechanics, producing new insights into the nature of singularities. Their research showed that singularities are not just a theoretical idea, but an inevitable reality in certain conditions, such as at the beginning of the universe or at the center of a black hole. Through their groundbreaking work, Hawking and Penrose demonstrated that if we rewind time all the way to the birth of the universe, we reach a moment where the curvature of space becomes infinite. At this point, time and space stop behaving according to normal laws. Essentially, the universe before the Big Bang was in a state where no recognizable space existed, and time as we know it simply didn't flow. In many ways, science has made tremendous strides in understanding the first moments of the universe. But the question of what happened before the Big Bang remains one of the greatest unsolved puzzles in modern physics. Theories vary, but many physicists argue that the very concept of before may not even apply, especially if time itself began with the Big Bang. Others believe that our inability to answer the question indicates that we have yet to uncover the right laws of physics to explain it. In our everyday experience, time feels like an unstoppable river, flowing relentlessly from one moment to the next. We can always ask what happened before yesterday, last year, or even 1,000 years ago. But when we apply this logic to the beginning of the universe, everything becomes far more complicated. At the heart of this confusion lies the singularity, a point where all the known laws of physics break down. Some scientists believe that time itself may have started at the moment of the Big Bang, meaning that there was no before at all. Asking what came before the Big Bang might be akin to asking what lies north of the North Pole. There simply is no direction beyond that point. This idea suggests that time, as we understand it, only exists within the universe and didn't exist before it. Yet not all scientists agree with this view. Some propose that the singularity may have arisen from something that existed prior to the Big Bang, perhaps a quantum fluctuation in an empty vacuum, where tiny, unpredictable shifts in energy triggered the birth of everything. Others speculate that our universe is part of a never-ending series of cycles, where a previous universe collapsed into a singularity, only to give birth to the Big Bang once again. These theories, highly speculative though they may be, offer tantalizing glimpses into what might exist beyond our current scientific understanding. And while many of them remain beyond our observational reach, they raise questions that are worth exploring. Stephen Hawking, one of the most famous scientists to grapple with these ideas, spent much of his career studying black holes, objects so dense that not even light can escape their gravitational pull. Black holes, like the Big Bang itself, contain singularities at their cores. In his groundbreaking research, Hawking made a surprising discovery. Black holes aren't completely dark, as once thought. Instead, they emit a faint form of radiation, now known as Hawking radiation, which suggests that black holes slowly lose mass and eventually evaporate over time. This radical idea challenged the prevailing belief that anything sucked into a black hole was lost forever. But it also raised a deeper question. Does information truly vanish into a black hole, or is there some unknown mechanism that allows it to be preserved? Studying singularities, whether in black holes or at the beginning of the universe, reveals a fundamental problem at the heart of modern physics. The two most powerful theories we have: Einstein's theory of general relativity, which governs the behavior of massive objects and cosmic structures, and quantum mechanics, which governs the behavior of particles on the smallest scales, simply do not work together in the extreme conditions found in singularities. Both theories break down in the face of the extreme gravity and densities present in a singularity, and scientists are now in search of a theory that can reconcile these two perspectives. Many physicists believe that quantum gravity, a unified theory that merges relativity and quantum mechanics, holds the key to understanding what happens inside black holes, what truly occurred during the Big Bang, and whether anything existed before it. For years, scientists have been working to create a complete theory that bridges these two pillars of physics, but this quest remains one of the greatest challenges in the field. Until such a theory is discovered, the greatest mysteries of our universe, what happened before the Big Bang, and what lies beyond the limits of space and time, will continue to intrigue and inspire generations of scientists and thinkers. However, despite the existence of countless theories and the development of sophisticated mathematical models, no one has yet managed to fully comprehend how gravity operates at the quantum level, the very foundation of the smallest building blocks of the universe. This remaining mystery makes it exceedingly difficult to grasp one of the most pivotal moments in the cosmos, the singularity at the dawn of the Big Bang. The singularity is not merely the birthplace of our universe, it also represents an intellectual boundary, a frontier that defies our current understanding. It marks the instant when time, space, and matter first materialized, yet it also stands as an insurmountable wall, a challenge to the very limits of scientific inquiry. In our daily lives, we experience reality through familiar constructs, cause and effect, the three-dimensional nature of space, and the linear progression of time. These are the foundations upon which our understanding of the universe is built. Yet the singularity forces us to confront the possibility that these very concepts may have no bearing in the moments before the Big Bang. It begs the question, what if the laws of physics we hold dear did not govern the universe before that initial moment? What if time itself, as we perceive it, did not exist before the birth of the universe? These questions not only challenge the foundations of modern physics, but also echo some of the most profound philosophical inquiries that have been asked for millennia. What is existence? How can something come from nothing? Can we ever truly comprehend the very instant when the universe was born? For thousands of years, thinkers from ancient philosophers to modern scientists have pondered these deep questions, and they remain at the core of humanity's relentless pursuit of knowledge. As technology advances and new discoveries are made, we are constantly pushing the boundaries of what we understand about the universe. Telescopes peer deeper into the vastness of space, particle accelerators reveal the fundamental components of reality, and theoretical models strive to unify the macrocosmic and the microcosmic into a single coherent understanding. Yet, despite these incredible advances, the singularity remains an enigma, a mystery that invites us to explore, to seek answers that may be beyond our grasp. And so we are left to venture further into one of the most intriguing and challenging ideas in cosmology: cosmic inflation. This mind-boggling event occurred mere moments after the Big Bang and has shaped everything we know about the universe today. Picture this. The universe in the aftermath of the Big Bang was a tiny, searing hot speck, expanding at a rate that defies human comprehension. In what seemed like the blink of an eye, the universe expanded faster than the speed of light. This event, cosmic inflation, was one of the most remarkable phenomena in the history of the cosmos, altering the very structure of reality in ways that we are still striving to understand. Cosmic inflation is not just an abstract theory. It provides the key to how our universe evolved from a minuscule, almost invisible dot into the vast, structured cosmos that we observe today. Without this theory, many aspects of the universe would remain inexplicable. To fully grasp the significance of inflation, we must first go back in time to a moment known as Planck time, just a fraction of a second after the Big Bang, when the universe was so small that it might have been smaller than a proton. And then something extraordinary occurred. Within the span of mere moments, the universe began expanding at an unprecedented rate. This is the essence of cosmic inflation. Between 1/1,000,000,000 of a second and 1/1000,000,000 of a second after the Big Bang, the universe expanded at an extraordinary pace, an expansion so rapid that it stretched space itself faster than the speed of light. To put this into perspective, imagine an atom stretching out to the size of an entire galaxy in less time than it takes to blink an eye. This exponential growth was not an explosion, as one might imagine from fireworks or matter flying apart. Rather, it was space itself stretching and expanding. And while this may seem paradoxical, it is allowed by the laws of physics, because it is not matter moving faster than light, but space itself that is expanding. And space, intriguingly, does not adhere to the same constraints as matter traveling through space. But inflation did more than just inflate the universe. It resolved some of the most perplexing puzzles in cosmology. For instance, when we look up at the night sky, the stars may appear scattered across the cosmos, seemingly at random. However, a closer look reveals something remarkable. The universe appears nearly identical, no matter where we look. The cosmic microwave background radiation, the faint afterglow from the Big Bang, has a nearly uniform temperature across the entire observable universe. This presents a challenge. If the universe began as a hot, dense point, why do distant regions of space appear so similar in temperature and structure? How could two far-off regions of the universe have the same characteristics despite being separated by billions of light years? This puzzle is known as the horizon problem, and it has long puzzled cosmologists. According to the traditional Big Bang model, there hasn't been enough time for light or heat to travel between distant regions of the universe to equalize them. Without inflation, the universe should show far more variation, with some areas much hotter or colder than others. Yet inflation solves this mystery by rapidly stretching space, enabling distant regions to interact with one another and equilibrate before being stretched apart. In essence, inflation allowed these far-off regions to be in contact for a brief moment, enough to even out the temperature and distribution of matter. Imagine a balloon with small bumps on it. If you were to inflate the balloon quickly, those bumps would stretch out and smooth over. In a similar way, the rapid expansion of space smoothed out the tiny irregularities in the early universe, creating the uniformity we observe today. But inflation did more than make the universe uniform. It also provided the foundation for the formation of galaxies, stars, and planetary systems. The rapid expansion set the stage for the intricate cosmic structures we observe today: galaxies, clusters of galaxies, and the vast filaments that span the universe. You might be wondering, is there any evidence that inflation really occurred? While cosmic inflation remains a theory, there is substantial evidence supporting it. One of the strongest pieces of evidence comes from the cosmic microwave background, CMB, the faint light that we can detect from the earliest moments of the universe. By studying the CMB, scientists have uncovered critical clues about the universe's infancy. One of the key predictions of inflation theory is the existence of tiny fluctuations in space and time, quantum ripples that occurred during the rapid expansion. Despite the overwhelming speed of inflation, these fluctuations persisted, and were stretched out to become large enough to influence the formation of galaxies, stars, and planets. When scientists observe the CMB, they can detect tiny temperature variations that are the remnants of these early fluctuations. These fluctuations are the fingerprints left behind by inflation. Without inflation, these variations would be much larger or might not exist at all. The close match between the predictions of inflation and the observations in the CMB provides strong evidence that inflation was indeed a real event. Moreover, inflation also helps to explain the flatness of the universe. When we examine the overall geometry of the universe, we find that it appears nearly perfectly flat. By flat, we mean that space is not curved like a sphere or distorted like a saddle. Rather, it follows the rules of ordinary geometry. This is puzzling because if the universe had begun randomly, it would likely be either curved or warped in some way. How did it end up being so flat? This is where inflation's role becomes crucial. The rapid expansion of the universe was so extreme that on the largest scales, it flattened out any initial curvature. In fact, when we measure the geometry of the universe today, we find it to be almost perfectly flat, just as inflation predicted. Finally, inflation played a vital role in the formation of galaxies and the large-scale structure of the universe. The tiny quantum fluctuations that occurred during the inflationary period were not random noise. They were the seeds of all the structures we see today. As the universe expanded and cooled, these fluctuations grew and eventually coalesced into clumps of matter. Gravity acted on these clumps, pulling them together to form the first stars and galaxies. Over billions of years, this process continued, shaping the universe into the vast, organized system we observe now. The intricate patterns of galaxies, clusters, and filaments that stretch across the cosmos match precisely what we would expect if inflation occurred. The tiny fluctuations from that early period were the building blocks for the cosmic structures we see today, and the rapid expansion of the universe provided the necessary conditions for their formation. Cosmic inflation is not just a theory. It is the key to understanding how our universe came to be, from its earliest moments to the magnificent structure we now observe. When we gaze into the vast, intricate tapestry of the cosmos, the immense structure of galaxies stretching across the universe, we're witnessing the product of an event that happened long ago. A series of tiny, almost imperceptible fluctuations in the fabric of space-time that were stretched out and amplified during a process known as cosmic inflation. Without inflation, it would be difficult, if not impossible, to explain how the universe took on the unique structure we observe today. The distribution of galaxies, their clustering in groups, and the vast spiderweb-like filaments that link them together. These patterns are not random. They are the direct result of the rapid expansion that occurred in the very early universe, a time when the cosmos was still in its infancy. The theory of inflation suggests that in the first moments of existence, the universe underwent an astonishingly rapid growth spurt, an expansion that was faster than the speed of light itself. This sudden burst laid the foundation for everything that would follow: the formation of galaxies, stars, and the large-scale structure of the universe. Inflation didn't merely shape the overall structure of the cosmos, it also explains the remarkable uniformity we observe across vast distances, even though the universe is not perfectly smooth. This uniformity is essential for the formation of the complex systems we see today, while the tiny imperfections, barely detectable at first, became the seeds of stars, galaxies, and even life itself. But what exactly is cosmic inflation? To understand it, let's journey back to the universe's very beginning, before there were stars, galaxies, or even atoms. In the first fraction of a second after the Big Bang, the universe was incredibly small and unimaginably hot. In this brief moment, it expanded at a pace that's almost beyond comprehension, stretching from smaller than a pinprick to vast scales in no time at all. This inflationary period was responsible for setting everything in motion, creating the initial conditions that would later lead to the universe we observe today. It wasn't just the size of the universe that changed, it was its entire structure and the fundamental forces that govern it. Inflation didn't just smooth out the universe, it also introduced the subtle variations that would later blossom into the stars and galaxies we know. These fluctuations, initially tiny and almost imperceptible, provided the seeds from which the large-scale structures of the universe would eventually form. Despite the fact that inflation remains a theory, its predictions are remarkably well supported by evidence. We see its fingerprints in the cosmic microwave background, CMB, the faint afterglow of the Big Bang that permeates the entire universe. The CMB carries the imprints of the inflationary period, offering us a snapshot of the universe in its infancy. The large-scale structure of the universe, with its galaxies and clusters, also fits perfectly with the predictions of inflation. So when we look at the universe today, at the stars, the galaxies, and even the vast empty spaces between them, we are seeing the legacy of that early cosmic event. It was during inflation that the groundwork for everything we experience was laid, from the formation of galaxies to the establishment of the fundamental forces that continue to govern our universe. Inflation stands as one of the cornerstones of modern cosmology, helping us understand how the universe, which began as an almost incomprehensibly tiny point, transformed into the vast, intricate cosmos we explore today. As we continue to delve deeper into space and uncover more about the origins of the universe, we will no doubt uncover further insights into the mysteries of creation. But for now, we can marvel at the extraordinary fact that, in the very first fraction of a second, the universe expanded at a speed we can barely imagine, setting the stage for everything that would follow. Every star, every planet, and even the atoms that form the very building blocks of life were once packed into an incredibly small, dense point in space. In an instant, the Big Bang occurred, and the universe burst into existence. This moment marked the beginning of the universe's evolution, and it raises one of the most fascinating questions of all. How did a burst of pure energy transform into the solid matter that makes up the stars, planets, and even life itself? This incredible transformation began in the first moments after the Big Bang. The universe at this stage was so hot and dense that conventional matter couldn't exist. Instead, it was an ocean of energy, an unstable, chaotic soup. But as the universe expanded and cooled, something extraordinary happened. The energy began to condense into particles. This is where Einstein's famous equation, E equals m squared, comes into play. According to this equation, energy and matter are interchangeable. As the universe cooled, energy began to be converted into the very building blocks of matter. However, for every particle that formed, an antiparticle appeared as well, its mirror image carrying the opposite charge. For each proton, an antiproton. For each electron, a positron. These antiparticles were almost identical to their counterparts, with one crucial difference: they carried opposite electrical charges. The universe in those early moments was a battleground, an intense, continuous battle of creation and destruction, with particles and antiparticles annihilating each other in a flash of pure energy. This constant annihilation should have resulted in a universe filled only with energy and no matter. No stars, no planets, no galaxies. So, why did matter survive? Why does anything exist at all? The answer lies in one of the greatest mysteries of physics, the matter-antimatter imbalance. For reasons we still don't fully understand, there was a slight imbalance between particles and antiparticles. For every billion antiparticles, there was one additional particle of matter. This tiny difference, just one extra particle for every billion, was enough to tip the balance in favor of matter. When the particles and antiparticles annihilated each other, the extra particles of matter were left behind, and they formed the universe we observe today. Without that infinitesimal imbalance, we wouldn't be here. Nothing would exist. Even after matter won its battle against antimatter, the universe was still a chaotic sea of particles, unable to form the stable, complex structures we're familiar with. The next monumental step in the universe's evolution was the formation of the first atoms, the basic building blocks of all matter. This event, known as nucleosynthesis, was one of the most critical moments in the history of the universe. In the early moments after the Big Bang, the universe was filled with a dense, hot soup of particles: protons, neutrons, electrons, and others. These particles collided with each other at immense speeds, but couldn't come together to form stable atoms. However, as the universe continued to expand, it began to cool, and within minutes, the temperature had dropped enough for the particles to finally begin fusing together. Protons and neutrons could now combine, creating the nuclei of the first elements in a process known as nuclear fusion. This fusion was the first step in the formation of matter as we know it. In the extremely hot conditions of the early universe, only the lightest elements could form. Within just a few minutes, three primary elements emerged: hydrogen, helium, and a trace amount of lithium. Hydrogen, the simplest and most abundant element in the universe, was created when a single proton attracted an electron, forming a stable hydrogen atom. Helium, the second most abundant element, formed when two protons and two neutrons fused together. A tiny amount of lithium was also produced, but it would play an important role in the formation of stars and planets later on. These three elements, hydrogen, helium, and lithium, accounted for nearly all of the matter in the universe at this stage. Yet the universe was still mostly empty. There were no stars, no galaxies, and no planets. It would take hundreds of millions of years for these simple atoms to come together under the force of gravity, forming the first stars. These stars, in turn, would become cosmic furnaces, fusing elements together and creating the heavier elements, carbon, oxygen, iron, that would eventually form planets, water, and life as we know it. The birth of the first elements was a turning point in the universe's journey. Without hydrogen and helium, there would be no stars. Without stars, there would be no heavier elements like carbon, oxygen, or iron, elements that are essential for the formation of planets, life, and everything we see today. Even today, hydrogen remains the most abundant element in the cosmos, making up about 75% of all visible matter, with helium accounting for most of the remaining 25%. These two elements continue to fuel stars, shaping the universe in ways that began billions of years ago. But the early universe was still far from the complex, structured cosmos we know today. The simple atoms that had just formed were waiting for gravity to take hold, to pull them together, and for the first stars to ignite. It would take time, but in those first crucial moments, the universe began its long, slow march toward complexity, a journey that would eventually lead to the birth of galaxies, planets, and life itself. The early universe was a chaotic and volatile place where energy, particles, and antiparticles danced in a turbulent ballet of creation and destruction. But through a series of remarkable events, from the era of inflation to the formation of the first atoms, the foundation for everything we know today was laid. It is a story of delicate balance, of tiny imperfections that shape the cosmos, and of forces that continue to govern the universe to this day. Without this subtle edge, the universe as we know it, its galaxies, stars, planets, and even life itself might never have come into existence. In the very early days of the cosmos, after the Big Bang, the universe was a vast, dark void, expanding rapidly. But everything changed when matter began to dominate, and a new chapter in the cosmic saga unfolded through a phenomenon known as nuclear synthesis. In this process, the simplest elements, hydrogen and helium, came into being. These were not just fleeting particles, they were the very building blocks of everything that would follow. Yet, despite the creation of these primordial elements, the universe remained a dark, empty expanse, devoid of the brilliant stars and planets we see today. It was a vast ocean of gas, stretching endlessly through the void. As time passed, gravity, the invisible force that binds everything together, began to work its magic. Slowly, it began to pull hydrogen and helium together, forming dense clouds of gas. In some regions of the universe, these clouds became so compact that the pressure and temperature skyrocketed, triggering a process that would forever change the fabric of existence: nuclear fusion. This was the spark that ignited the first stars, colossal glowing spheres of burning gas. These stars, bright and fierce, marked the end of the universe's cosmic dark ages. These first stars were not just points of light, they were the crucibles of creation. Within their fiery cores, nuclear reactions fused lighter elements into heavier ones: carbon, oxygen, iron, and countless others. These elements, which would later form the foundation for planets, oceans, and life itself, were forged in the heart of these ancient stars. But their lives were brief. When these stars reached the end of their life cycle, they exploded in violent supernovae, scattering the newly created elements into the surrounding space. This explosion enriched the cosmos, creating the raw materials necessary for the birth of a new generation of stars and planets. With more heavy elements now available, new stars began to form. These stars were often surrounded by swirling disks of dust and gas, remnants of earlier explosions. Over millions of years, these particles clumped together, giving rise to planets, moons, and asteroids. On some planets, such as Earth, conditions were just right for the formation of atmospheres and oceans, setting the stage for life to emerge. Every single atom in our bodies, the oxygen we breathe, the calcium in our bones, the iron in our blood, was once part of a distant star that lived and died billions of years ago. The story of the universe is, in many ways, the story of us, written in the language of stardust, etched across the vast stretch of time. But this is not the end. The universe continues to evolve. Galaxies collide, new stars are born, and planets continue to form. As we look deeper into the cosmos, we uncover more mysteries: black holes, dark matter, and the possibility of life beyond our own planet. The universe is so vast, so complex, and so breathtakingly beautiful that it constantly leaves us in awe of its endless wonders. When we gaze up at the night sky, we see a dazzling array of stars scattered across the dark canvas of space. These tiny points of light twinkle and shine, a reminder of the immense universe that surrounds us. But have you ever wondered how these stars came into being? How did they form from the cold emptiness of space? This is the remarkable story of star formation. A tale of how stars are born, how they live, and how they eventually die in spectacular explosions that illuminate the cosmos. Stars are not just beautiful ornaments in the sky, they are the very engines that power the universe. Their energy fuels the creation of new elements, provides light to distant planets, and even shapes the galaxies in which they reside. To understand how stars form, we need to start by looking at the regions where they are born. The stellar nurseries, or nebulae. These are vast clouds of gas and dust, often stretching for light years, scattered throughout the galaxy. They are the cosmic factories where new stars are made. But these nebulae are not static. Over millions of years, something extraordinary begins to happen. Gravity, that invisible force that binds everything together, starts to pull the gas and dust inward. As this material collapses, it heats up and becomes denser. The particles within the cloud begin to collide, compressing further and raising the temperature. This marks the beginning of the birth of a star. Amidst the swirling gas and dust, a baby star begins to emerge. This is known as a protostar. At this stage, the protostar is still too cool to shine like the stars we see twinkling above us. It hasn't yet reached the extreme temperatures required to ignite nuclear fusion, but the process of becoming a fully fledged star is underway. As the protostar continues to collapse, its core grows hotter and denser. Eventually, the temperature reaches around 10 million degrees Celsius, and nuclear fusion begins. This marks the true birth of a star. At this moment, the hydrogen atoms in the protostar's core begin to fuse into helium, releasing an incredible amount of energy in the process. This energy pushes outward, creating an immense force that resists the pull of gravity, which is trying to collapse the star inward. This balance between the outward pressure from fusion and the inward pull of gravity is what allows a star to remain stable. For millions or even billions of years, this delicate equilibrium keeps the star shining brightly. This constant tug-of-war between gravity and the energy generated by nuclear fusion is the essence of a star's life. It's what gives stars their light and warmth. Over time, this balance allows stars to continue shining, their light illuminating the vast reaches of space. But like everything in the universe, a star's life does not last forever. Eventually, even the most powerful stars will run out of fuel. When this happens, they begin to die. The death of a star is as spectacular as its birth. When a star runs out of hydrogen to burn, it can no longer sustain the pressure required to keep it stable. Depending on its mass, the star may expand into a red giant or collapse into a white dwarf, neutron star, or even a black hole. For massive stars, their death is marked by an explosive supernova, sending shockwaves of energy and newly created elements throughout space. These explosions create the conditions for new stars and planets to form, continuing the endless cycle of creation and destruction that drives the evolution of the cosmos. The life of a star is a journey through chaos and beauty. From the swirling gas clouds of stellar nurseries to the magnificent explosions of dying stars, the journey of a star is a never-ending cycle of birth, life, and death. It is a cosmic dance that shapes the universe itself, creating the elements that make up everything we know: planets, oceans, and even life. Stars, brilliant and beautiful, live lives that are far more complex than we often realize. Their ultimate fate depends largely on one key factor: their mass. In this exploration, we delve deeper into the incredible lives of stars, examining how their size determines how they live, age, and eventually die. Most stars spend the majority of their lives in a phase known as the main sequence. During this phase, stars fuse hydrogen into helium in their cores, releasing vast amounts of energy in the process. This energy is what makes stars shine. Our own sun is a main sequence star, and it has been burning through hydrogen for about 4.6 billion years. Yet, like all stars, its time will eventually come to an end. But the cycle of creation will continue, and the story of the universe will unfold, one star at a time. The mass of a star plays a critical role in determining how long it will remain in its stable phase, and this difference in mass leads to vastly different life cycles. Smaller stars, known as red dwarfs, burn their fuel at an incredibly slow pace, without rushing the process. As a result, they enjoy a calm, steady existence that lasts for trillions of years. Their longevity seems almost unimaginable compared to the fleeting lives of larger stars, which consume their fuel much more rapidly. These massive stars live fast and burn bright, but their lives are short-lived, often lasting only a few million years before exhausting their hydrogen fuel. Once a large star like a blue giant runs out of hydrogen, its fate takes a dramatic turn. The end of hydrogen burning marks the beginning of a remarkable transformation, and from here, the star's future splits into two very distinct paths, dependent on its size. For stars with a mass similar to our Sun, classified as low to medium mass, death arrives much more gently. As these stars run out of fuel, they don't explode. Instead, their cores shrink due to the overwhelming force of gravity, while their outer layers expand massively. This expansion leads to the formation of a red giant, a bloated, swollen version of its former self. During the red giant phase, the star sheds its outer layers into space. The material that was once part of the star becomes a beautiful glowing cloud of gas and dust, known as a planetary nebula. This nebula represents the last remnants of the star's outer layers, leaving behind only its hot, dense core. Over time, this core cools and fades, slowly transforming into a white dwarf. Despite being roughly the size of Earth, a white dwarf is incredibly dense. It packs the mass of the sun into a small, compact space. Over the course of billions of years, this white dwarf will continue to cool and dim, eventually becoming a black dwarf. This process is extraordinarily slow, and the white dwarf will fade away, leaving behind nothing but cold darkness in the void. For stars much larger than our sun, however, the end is far more violent and dramatic. These massive stars burn through their fuel at breakneck speed, racing toward an inevitable and cataclysmic conclusion. After exhausting their hydrogen, they begin to fuse heavier elements such as helium, carbon, and even iron. But here's the twist. Iron, unlike other elements, cannot undergo fusion to release energy, and since energy is what keeps a star stable, the absence of this energy source leads to the collapse of the core under its own immense gravity. This collapse occurs almost instantaneously, and it is this event that triggers a supernova, the most spectacular and energetic explosion in the universe. The supernova is so powerful that it sends shockwaves rippling through the star, blasting its outer layers into space. This massive explosion releases more energy in a single instant than our sun will emit over its entire lifetime. But the brilliance of the explosion is just the beginning. Supernovae are not only awe-inspiring displays of light, they play a crucial role in the universe's grand design. They create the very elements that make up the universe we see today. In the heart of dying stars, elements heavier than iron, such as gold, silver, and uranium, are forged in the intense heat of the explosion, and these elements are scattered across space. In doing so, supernovae enrich the cosmos, setting the stage for the birth of new stars, planets, and even life itself. The process doesn't end with the explosion. What remains after a supernova depends on the mass of the core left behind. If the core is between 4 and 3 times the mass of our sun, it doesn't simply vanish. Instead, it collapses into a neutron star, an incredibly dense object where the matter is packed into an unbelievably small space. To put it into perspective, just a teaspoon of neutron star material would weigh more than 1 billion tons on Earth. These stars are extreme in every sense, rotating at staggering speeds, and some become pulsars, emitting powerful beams of radiation into space like cosmic flashlights. But if the star's core is even more massive, the collapse doesn't stop at the neutron star stage. The core compresses further, creating one of the most mysterious and terrifying objects in the universe: a black hole. The gravitational force around a black hole is so immense that not even light can escape its pull. The star's remaining matter is crushed into a point of infinite density known as a singularity. At this point, the known laws of physics break down, and what happens inside a black hole remains one of the greatest mysteries in science. While a massive star's death marks the end of one life, it also ushers in the birth of objects that stretch our understanding of the cosmos. Neutron stars and black holes are the extraordinary remnants of dying stars, objects that represent both the immense power and the unfathomable chaos that characterize the universe. Stars, however, do not live in isolation. They are part of something much larger, an intricate and vast system known as galaxies. Galaxies are colossal cosmic cities made up of stars, gas, dust, and dark matter, all bound together by gravity. Our own galaxy, the Milky Way, is just one of trillions that populate the universe. But how did these massive collections of stars come into existence in the first place? The formation of galaxies began long ago in the early universe, not with the sudden appearance of stars, but from immense clouds of gas. These clouds, containing vast amounts of dust and gas, were pulled together by gravity. As the gas collapsed, it began to spin, eventually forming flat, rotating disks that gave birth to the first stars. This was the birth of the first galaxies, the foundational building blocks of the complex cosmic structures we observe today. As galaxies formed, they did not remain static. They interacted with each other, colliding, merging, and evolving over billions of years. These interactions shaped the universe into the complex web of stars, planets, and galaxies that exists today. Studying these interactions allows us to begin to understand the larger processes that govern the universe and how it evolved into the vast and dynamic space we see before us. Galaxies, in fact, are not random collections of matter. They are the product of a fascinating and intricate process of formation, guided by invisible forces that shape the universe. One of the most important and mysterious of these forces is dark matter. Dark matter is a substance that cannot be seen. It does not emit light, nor does it interact with electromagnetic forces in the way that regular matter does. Despite being invisible, dark matter has a profound impact on the universe. It makes up the majority of the mass in galaxies, and its gravitational influence is the invisible scaffolding that holds galaxies together. Without dark matter, galaxies would not have the gravity necessary to remain intact. In this sense, dark matter acts like the unseen glue that holds galaxies, and indeed, the very structure of the universe, together. This process of galaxy formation, which began in the early stages of the universe, is still unfolding today. Gas clouds started to form long ago, and as they were pulled together by gravity, they created the first proto-galaxies, early building blocks of the galaxies we see now. These proto-galaxies eventually merged and evolved into the galaxies we observe across the cosmos, their formation and interactions guided by the unseen forces of dark matter. Through this grand cosmic dance, galaxies have shaped the universe into the ever-changing and breathtakingly complex structure we see today. Over time, the universe's earliest structures, known as proto-galaxies, began to evolve, gradually transforming into full-fledged galaxies. Some of these galaxies assumed the familiar spiral shapes we see today, like our very own Milky Way, while others took on more spherical forms, resulting in elliptical galaxies. However, galaxies don't simply form in isolation. They are part of a larger cosmic drama, interacting with each other in profoundly dramatic ways. These interactions can be violent, with galaxies colliding, merging, and influencing each other's shape and evolution. The forces at play during these collisions are immense. When galaxies crash into one another, the gas within them also collides, creating shockwaves that trigger bursts of star formation. This process, born from the immense energy released during such collisions, causes the gas clouds to condense, forming new stars. The results are often spectacular. Some of the most breathtaking and dynamic galaxies we observe today, known as starburst galaxies, are direct consequences of these energetic cosmic crashes. Our own Milky Way is not immune to this cosmic dance. In fact, it is on a collision course with the Andromeda Galaxy. About 4 billion years from now, these two galaxies will collide and eventually merge into one enormous galaxy, a colossal transformation that will irrevocably change the night sky as we know it. It is hard to imagine exactly what this event will look like, but it is certain to be one of the most spectacular and unforgettable transformations in the history of the universe. Even as galaxies grow, evolve, and collide, they are all intricately linked by a vast, invisible structure known as the cosmic web. This is an enormous network stretching across the entire universe, composed of galaxies, gas, and dark matter, interwoven like the threads of a massive cosmic tapestry. The cosmic web is built from enormous filaments of dark matter and gas that connect galaxies, creating a vast network that shapes the large-scale structure of the cosmos. The cosmic web serves as the framework within which galaxies exist, grow, and evolve. This interconnectedness between galaxies and dark matter is crucial for understanding the universe's structure. The way galaxies form, evolve, and interact dictates the cosmic landscape, influencing everything from the birth of stars to the formation of vast galaxy clusters. Within each galaxy, stars are born, live out their lives, and die, continuing the endless cycle of creation and destruction that defines the universe. Stars are born from clouds of gas, their lives unfolding in various forms and sizes before they ultimately die, often in spectacular and explosive events. The birth of stars, their explosive death in supernovae, and the ongoing formation of galaxies are all part of the relentless interconnected process of cosmic evolution. The universe itself is in constant motion, a dynamic system where stars are born and die, galaxies collide and merge, and dark matter silently holds everything together, guiding the evolution of the cosmos. At the heart of these processes lies dark matter, an enigmatic and invisible substance that plays a critical role in the structure and evolution of the universe. Although we cannot see dark matter directly, because it does not interact with light or any other form of radiation, we know it exists due to the peculiar gravitational effects it has on visible matter. These effects are particularly noticeable when studying phenomena like the formation and movement of galaxies, the bending of light around massive objects, a phenomenon known as gravitational lensing, and the dynamics of galaxy clusters. Dark matter also reveals its presence in the cosmic microwave background radiation, the faint afterglow of the Big Bang that still lingers in the universe today. According to the lambda cold dark matter, lambda CDM model, which is the most widely accepted cosmological model, the universe is composed of roughly 5% ordinary matter, the kind that makes up stars, planets, and everything we can see, 26.8% dark matter, and 68.2% dark energy. This means that dark matter accounts for approximately 85% of the total mass in the universe, while dark energy and dark matter together make up about 95% of the universe's total energy content. Despite its importance, the nature of dark matter remains one of the greatest mysteries in modern astrophysics. It doesn't interact with regular matter or light, making it extremely difficult to detect using current technology. However, scientists believe that dark matter may consist of tiny, as yet unknown particles, such as weakly interacting massive particles, WIMPs, or axions. Another theory proposes that dark matter could be composed of ancient black holes formed in the early stages of the universe. Dark matter can also be classified according to how quickly its particles move. Most scientists believe dark matter is cold, meaning its particles move slowly, allowing them to clump together and form the large structures we see in the universe today. While the existence of dark matter is almost universally accepted by astrophysicists, there remains a small group of scientists who challenge the idea, pointing to certain observations that dark matter does not fully explain. These scientists have proposed alternative theories, such as modified Newtonian dynamics, MOND, suggesting that perhaps the laws of gravity need to be adjusted. However, these alternative theories have yet to offer a comprehensive explanation for all the observed phenomena, indicating that dark matter, despite its elusive nature, remains a necessary component of our understanding of the universe. The story of dark matter is deeply intertwined with the history of modern astronomy, and its origins date back more than a century. In the late 19th century, in 1884, the British physicist William Thomson, better known as Lord Kelvin, made several intriguing observations about the stars around our sun. In a lecture series, Kelvin tried to estimate the density of stars near the sun. And using this data, he speculated that if there were 1 billion stars within a certain distance, the way these stars moved would be difficult to explain. This idea set the stage for later theories on invisible matter in space. In the early 20th century, in 1906, French mathematician and physicist Henri Poincaré introduced the term dark matter, or matière obscure, while discussing Lord Kelvin's work. Poincaré suggested that there might be hidden mass in the universe, though he believed this invisible matter would be far less abundant than the visible matter we can see. His concept of dark matter sparked further discussions in the scientific community. The idea continued to evolve over the years. In the 1920s, Dutch astronomer Jacobus Kapteyn became one of the first to use star velocities to hint at the presence of dark matter. He observed that the way stars moved in space could be influenced by unseen forces, suggesting the presence of an invisible mass. A decade later, in 1930, Swedish astronomer Knut Lundmark expanded on this idea, proposing that the universe must contain much more mass than could be detected with existing telescopes, revealing that the visible universe might not be the complete picture. Then, in 1932, another Dutch scientist, Jan Oort, entered the conversation. He studied the movements of stars near our galaxy and concluded that there must be more mass in the Milky Way than could be seen. This was another key observation that helped solidify the idea of dark matter and paved the way for future discoveries about the mysterious invisible substance that continues to shape the universe today. The mystery of dark matter has intrigued scientists for nearly a century. Its existence was first hinted at in the early 20th century when astronomers began noticing that the mass observed in galaxies and clusters seemed insufficient to account for the way they behaved. In the beginning, the idea of invisible matter exerting gravitational forces on visible matter was only a speculative hypothesis. But as research advanced, this hypothesis gradually gained more support, leading to a profound shift in our understanding of the universe's structure. Initially, the problem arose when astronomer Fritz Zwicky, working at the California Institute of Technology, began studying the dynamics of galaxy clusters. In 1933, while investigating the Coma cluster, he noticed something puzzling. The galaxies in the cluster were moving much faster than expected, based on the visible mass he could observe through his telescope. According to the laws of gravity, galaxies should have been moving more slowly, considering the amount of visible matter in the cluster. Yet, their rapid motion suggested the presence of some unseen force holding the galaxies together. Zwicky, driven by this strange observation, proposed the existence of what he called dunkel materie, dark matter. Zwicky's calculations were groundbreaking, suggesting that the Coma cluster possessed roughly 400 times more mass than could be accounted for by the visible stars. He believed that this invisible mass was the key to the gravitational forces binding the galaxies within the cluster. Although Zwicky's estimates were later shown to be incorrect, due in large part to the outdated values of the time, he remains one of the first scientists to recognize that the universe might be filled with invisible mass, exerting gravitational pull on the objects we can see. However, Zwicky's interpretation of dark matter was different from our modern understanding. He theorized that dark matter was simply ordinary matter that did not emit light, rather than the mysterious and fundamentally different substance we now suspect dark matter to be. While Zwicky did not define dark matter in the way we understand it today, his work was an important early step in the investigation of this elusive force. As the decades passed, more evidence began to accumulate, further supporting the existence of dark matter. One of the key breakthroughs came in 1939 when H.W. Babcock studied the rotation of the Andromeda Galaxy. The Andromeda Galaxy, as the closest spiral galaxy to Earth, was a prime subject for observation. Babcock's study revealed that stars at the galaxy's outer edges were moving much faster than anticipated based on the visible matter. This suggested that there was far more mass in Andromeda than could be seen with the telescope. Initially, Babcock proposed that the unusual motion could be caused by light being absorbed within the galaxy or by the possibility that the dynamics of the galaxy were different at its edges. Yet, his observations hinted at something more. An invisible influence was at work, affecting the galaxy's rotation. The following year, in 1940, another significant discovery was made by Jan Oort. He studied a galaxy called NGC 3115 and found a large, invisible halo of mass surrounding it. This discovery further bolstered the idea that galaxies might contain hidden matter beyond what we could observe. Oort's findings supported the idea that galaxies could be enveloped by massive halos of unseen mass, potentially influencing their behavior. The 1970s marked a turning point in the study of dark matter, as more scientists began to converge on the idea that galaxies might be surrounded by vast halos of invisible mass. Independent research from groups in both Princeton, New Jersey, and Tartu, Estonia, in 1974 arrived at similar conclusions, strengthening the theory that dark matter was a reality. Key observations of galaxies' rotation further reinforced this idea. Vera Rubin and Kent Ford, working with new spectrograph technology, were able to make more accurate measurements of the velocities of stars in spiral galaxies. Their findings revealed unexpected results in the rotation curves of these galaxies. Meanwhile, astronomers in the field of radio astronomy were observing the 21 centimeters line of atomic hydrogen, a crucial tool for understanding the mass distribution in galaxies. Unlike starlight, which is concentrated at the galactic center, hydrogen gas extends far beyond the visible edges of a galaxy. This provided astronomers with a more complete picture of the galaxy's total mass. Studies of the Andromeda galaxy using massive telescopes, like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen rotation curve didn't match what was expected based on Kepler's laws. Kepler's laws dictate how objects move around a center of mass, and the discrepancy suggested something invisible was influencing the galaxy's motion. By 1975, astronomers like Roberts and Whitehurst were pushing the boundaries even further. They measured the rotational velocity of stars in Andromeda up to distances of 30 kiloparsecs, about 98,000 light-years. Their results revealed a surprising finding. The rotation curve of the galaxy remained flat at these great distances. This indicated that there was far more mass present in the outer regions of the galaxy than could be explained by visible stars alone. The rotation curve, as plotted in their charts, showed that the cumulative mass continued to increase even in the galaxy's most distant regions, suggesting that dark matter extended well beyond what could be observed. By the end of the 1970s, it had become widely accepted that galaxies were likely surrounded by invisible halos of dark matter. This realization became one of the most significant mysteries in modern astronomy. In the 1980s and 1990s, further studies solidified the theory. One pivotal study in 1996, conducted by Persic, Salucci, and Stellized, analyzed 167 spiral galaxies and found strong evidence for the presence of dark matter in their outer regions. Additional observations provided further confirmation. Gravitational lensing, where galaxy clusters bend light from distant objects, revealed the presence of unseen mass. The distribution of hot gas in galaxies and galaxy clusters, as well as the tiny temperature fluctuations called anisotropies, observed in the cosmic microwave background radiation, the afterglow of the Big Bang, all pointed toward the existence of dark matter. By the early 21st century, most scientists agreed that dark matter is composed of particles that have yet to be discovered. These particles are thought to be unlike anything in the standard model of particle physics, and finding them has become one of the primary goals of contemporary research in particle physics. Various experiments, such as those using particle accelerators and underground detectors, continue to search for these elusive particles with the hope of uncovering one of the universe's greatest secrets. At its core, the term matter in cosmology refers to anything that contributes to the overall energy of the universe. As the universe expands, the density of matter decreases in a specific way, proportionally to the cube of the expansion. This means that as the universe grows, matter becomes more spread out. Radiation, in contrast, decreases even faster in intensity as the universe expands, losing energy according to the inverse fourth power of the expansion. The cosmological constant, however, remains unaffected by the expansion of the universe as it is a property of space itself. It does not change no matter how much the universe stretches. Dark matter is often discussed in terms of invisible mass that exerts gravitational influence but does not emit or interact with light in the same way as regular matter. While this matter behaves like regular matter in terms of its gravitational pull, it is likely composed of particles that differ fundamentally from those we encounter every day. In some cases, dark matter refers to the possibility of missing baryons, a form of ordinary matter that does not emit light. But the most widely accepted explanation is that it consists of particles that have yet to be identified. One of the major observational challenges with dark matter arises from the way galaxies rotate. In spiral galaxies, the stars and gas at the center of the galaxy experience the strongest gravitational pull, while the outer stars and gas are pulled more weakly. If all the mass in a galaxy were visible, the rotation of stars and gas would behave according to Kepler's third law, much like the planets in our solar system. This law predicts that the farther a star is from the center of a galaxy, the slower its rotation should be. However, this is not the case. Instead, stars and gas on the outskirts of galaxies often move at faster speeds than expected, or the rotation speeds remain constant even at extreme distances from the galactic center. This discrepancy suggests that there is more mass in the outer regions of galaxies than is visible. It is believed that much of this mass is invisible, and it is this dark matter that explains the observed rotation patterns. In bound systems like galaxies, the movement of stars is also governed by the virial theorem, which provides insight into how mass is distributed in such systems. When scientists examine the motion of stars in systems like elliptical galaxies or dense star clusters, they can apply this theorem to determine how mass is spread throughout the system, confirming that dark matter plays a crucial role in maintaining the structure of galaxies. As we continue to probe the nature of dark matter, its presence remains one of the most profound enigmas in astrophysics. In many cases, the speeds we observe within galaxies or galaxy clusters don't align with the mass that we can visibly account for. Even when we consider the intricate orbital patterns of stars, these observed speeds often defy expectations based on the amount of visible matter in the system. Much like the enigmatic rotation curves of galaxies, the mismatch between predicted and observed speeds leads scientists to propose the presence of something unseen, something that has yet to reveal itself through conventional means. The most reasonable explanation for this discrepancy? Dark matter. Galaxy clusters, dense regions of the universe containing hundreds to thousands of galaxies, are pivotal in our understanding of dark matter. They serve as cosmic laboratories where dark matter's influence becomes clearer. Researchers have three primary methods for measuring the total mass of a galaxy cluster: by observing the range of speeds at which the galaxies move, by studying the X-rays emitted by the hot gas that permeates the cluster, and by analyzing gravitational lensing, the bending of light due to the mass of the cluster. When scientists observe galaxy clusters, they first look at the movement of the galaxies within the cluster. By calculating the speeds at which these galaxies orbit one another, they can estimate the total mass of the cluster. But the mass derived from the galaxy's velocities often falls short when compared to the amount of visible matter within the system, suggesting that an invisible form of mass must be at play. This is the suspected dark matter. Next, scientists turn to the hot gas inside the cluster. This gas emits X-rays, and by studying these X-rays, researchers can determine its temperature and density. From this, they can calculate the pressure within the cluster and, using the delicate balance between gravity and pressure, estimate the cluster's total mass. These measurements consistently point to a conclusion. Dark matter accounts for roughly 5 times the mass of all visible matter in these clusters. The third method of mass measurement is perhaps the most dramatic and fascinating: gravitational lensing. A phenomenon predicted by Einstein's theory of general relativity, Gravitational lensing occurs when the light from a distant object is bent by the gravitational field of a massive object, such as a galaxy or a galaxy cluster, that lies between the observer and the light source. Gravitational lensing is particularly intriguing because it only requires the presence of mass, no matter the type of mass. The more massive an object is, the more it will bend the light passing through its gravitational field. This bending distorts the light, creating visual phenomena like arcs or magnified images of distant galaxies. For instance, imagine a galaxy cluster lying between Earth and a distant quasar. As light travels from the quasar, the massive galaxy cluster warps the light, distorting the quasar's image. This process allows scientists to measure the mass of the galaxy cluster without directly observing the motion of the galaxies within it. In the case of strong gravitational lensing, the distortion is so pronounced that light from distant galaxies can form arc-like shapes around the cluster, revealing the structure of the cluster itself. One notable example of this is the galaxy cluster A1689, where such arcs have been observed in abundance. By studying the shapes of these arcs, scientists can estimate the mass of the galaxy cluster that caused the distortion. Weak gravitational lensing, in contrast, is subtler. Here, the bending of light is much less noticeable, leading to only minor distortions in the shapes of galaxies. However, these tiny shifts provide valuable insights into how dark matter is distributed in the universe. Over time, these subtle changes have helped scientists piece together the large-scale structure of dark matter in the cosmos. Dark matter and ordinary matter, though both forms of matter, behave in strikingly different ways. Ordinary matter, composed of protons, neutrons, and electrons, interacts strongly with light. This interaction causes it to scatter, making it visible. Dark matter, however, does not interact with light in the same way. It is invisible to our eyes and most other detection methods. But dark matter's presence is undeniable. For example, its gravitational influence can be felt across the universe, especially on the cosmic microwave background, CMB, the faint glow of radiation left over from the Big Bang. The CMB offers a snapshot of the universe just 380,000 years after its birth. It is incredibly uniform, with slight temperature fluctuations that provide clues about the universe's early structure. These fluctuations are minute, on the order of 1 part in 100,000, but they are crucial for understanding how the universe evolved. These tiny temperature differences, known as anisotropies, can be mapped across the sky. By analyzing these fluctuations, scientists can construct a graph called the angular power spectrum. This graph reveals a series of peaks, evenly spaced but varying in height. The positions and heights of these peaks tell scientists about the fundamental parameters of the universe, factors like the amount of ordinary matter, and dark energy. The first significant discovery of these anisotropies came in 1992 when the COBE satellite detected them, though its resolution was not fine enough to reveal the detailed peaks. It wasn't until 2000, with the boomerang experiment, conducted using a balloon to take measurements, that the first distinct peaks were observed. Later, the WMAP and Planck satellites provided even more precise measurements, confirming key cosmological models, most notably the Lambda Cold Dark Matter, LCDM model. This model suggests that structure formation, the process by which galaxies, stars, and clusters of galaxies formed, began soon after the Big Bang. Before this period, the universe was nearly uniform. The density of matter was spread evenly across space. But tiny fluctuations in this density, driven by quantum fluctuations in the early universe, began to grow over time. These minuscule irregularities became the seeds for the structures that would eventually form the galaxies and clusters of galaxies that we see today. However, radiation dominated the early universe, and its influence was profound. Radiation kept ordinary matter's density fluctuations from growing large enough to form the structures we observe in the universe today. If the universe consisted only of ordinary matter, these fluctuations would not have been able to evolve into the complex cosmic structures, stars, galaxies, and clusters that we see now. Dark matter, which interacts only through gravity and does not interact with radiation, was key to allowing these fluctuations to grow. As dark matter clumped together under its own gravity, it created gravitational wells that pulled ordinary matter into them. These wells acted as cosmic magnets, speeding up the formation of galaxies, stars, and other cosmic structures. Without dark matter's gravitational influence, the universe would look very different today, likely lacking the rich and varied structures we observe across the cosmos. A striking example of dark matter's influence can be seen in the Bullet Cluster, a system formed by the collision of two massive galaxy clusters. The Bullet Cluster is particularly fascinating because it reveals a significant difference between where visible matter and dark matter are located. According to gravitational lensing, the mass of the cluster is located in one region, but the visible matter, such as gas and galaxies, exists in a separate region. This separation is difficult to explain through alternative gravity theories, which would expect gravitational lensing to occur only around visible matter. However, the standard theory of dark matter easily accounts for this discrepancy. In the aftermath of the collision, visible gas was slowed down by electromagnetic forces, while the dark matter passed through largely unaffected, creating two distinct lensing peaks. Astronomers also use Type 1a supernovae, explosions of white dwarf stars, to measure distances across the universe. These supernovae are considered standard candles because their intrinsic brightness is well understood. By measuring how dim they appear from Earth, scientists can calculate their distance from us. The observations from these supernovae have led to the discovery that the universe is expanding at an accelerating rate. This acceleration is often attributed to the mysterious force known as dark energy. Finally, we come to the concept of baryon acoustic oscillations, BAO, which refer to periodic fluctuations in the density of ordinary matter in the early universe. These oscillations were created by sound waves traveling through the hot, dense plasma of photons and baryons before the universe cooled enough for atoms to form. The imprint of these oscillations can still be observed in the cosmic microwave background radiation. Over time, as the universe expanded, dark matter and ordinary matter began to clump together, but the effects of the original sound waves weakened, leaving behind traces that scientists continue to study today. Through these myriad observations, we are slowly piecing together the mysterious puzzle of dark matter, a puzzle that continues to elude direct detection, but whose effects are felt across the universe. From the rotation curves of galaxies to the formation of large-scale cosmic structures, dark matter is an invisible but undeniable presence that shapes the very fabric of our universe. However, if we look closely at the universe, we can still detect a subtle but significant pattern in the distribution of galaxies. These massive cosmic structures appear to be spaced roughly 147 million light-years apart. This isn't just a random coincidence, rather, it is a measurable signature of early oscillations that occurred in the infant universe. This pattern, first predicted in the 1990s, was confirmed in 2005 through large-scale surveys like the Sloan Digital Sky Survey, SDSS, and the 2-degree Field Galaxy Redshift Survey, 2DFGRS. By combining observations from the cosmic microwave background, CMB, with baryon acoustic oscillation, BAO, measurements, scientists can estimate crucial cosmic values, such as the rate at which the universe is expanding and the amount of matter it contains. These results offer strong support for the lambda cold dark matter, lambda CDM model, the prevailing cosmological theory today. When researchers observe the redshifts of galaxies, they are effectively mapping out the universe's three-dimensional structure, revealing how galaxies are distributed across vast cosmic distances. But this mapping isn't without its challenges. The distances that we estimate for these galaxies are not exact, but are instead based on their redshift, essentially how much their light has stretched due to the expansion of the universe. The redshift we observe is affected by two primary factors: the universe's overall expansion and the peculiar motion of individual galaxies. The latter refers to the velocity of a galaxy relative to the average cosmic flow, often known as its peculiar velocity. On large scales, galaxies tend to cluster together, forming superclusters, vast regions of space packed with multiple galaxies. These superclusters grow more slowly than the overall expansion of the universe because their collective gravity pulls matter toward them. In contrast, voids, those enormous empty spaces between galaxies, are expanding faster than the universe itself. This differential expansion creates interesting and observable effects. For instance, galaxies that lie in front of a supercluster tend to move towards it more rapidly than expected, meaning their redshift will be slightly higher than anticipated. On the other hand, galaxies situated behind a supercluster exhibit a lower than expected redshift. These variations cause superclusters to appear somewhat flattened along our line of sight, while voids seem stretched. Although this effect is challenging to detect in individual structures, as we cannot precisely determine their shapes, astronomers can analyze large data sets by averaging observations across multiple structures. The first prediction of this phenomenon was made by cosmologist Nick Kaiser in 1987, and it was confirmed in 2001 by the 2D FGRS, which produced results that aligned with the lambda CDM model. In a related area of cosmological research, the Lyman alpha forest is a crucial tool for understanding the universe's evolution. This phenomenon refers to a series of absorption lines observed in the spectra of distant galaxies and quasars. These absorption lines are caused by neutral hydrogen atoms absorbing light at a specific wavelength, an event known as the Lyman alpha transition. By studying these absorption lines, astronomers can refine our understanding of cosmological models, with results that consistently match the predictions made by the WMAP, Wilkinson Microwave Anisotropy Probe data. When it comes to dark matter, scientists often categorize it into three main types: cold, warm, and hot. However, these terms don't refer to temperature, but rather to the velocity of the particles in question during the early universe. In simple terms, these labels describe how far the particles could travel due to random motions before the universe began to expand. This distance is known as the free streaming length, FSL. The classification of dark matter depends on how the FSL compares to the size of a protogalaxy, an early cosmic object that would eventually become a small galaxy. Cold dark matter, CDM, is characterized by particles with a very short free streaming length relative to the size of a protogalaxy. Warm dark matter, WDM, occurs when the FSL is roughly the same size as a protogalaxy. Hot dark matter, HDM, applies to particles whose free streaming length is much larger than the size of a protogalaxy. In the mid-1990s, there were theories suggesting a mix of these types of dark matter. However, these ideas have become less popular since the discovery of dark energy, which has reshaped our understanding of cosmic expansion. The importance of the free streaming length lies in the fact that the universe's early fluctuations in density, caused by tiny quantum variations at the smallest scales, played a major role in shaping the structure of the cosmos. As particles moved from denser areas to less dense regions, the rapid expansion of the universe imposed a limit on how far they could travel. Faster-moving particles, like those in hot dark matter, were able to travel further before the universe expanded too much, while slower-moving particles, such as those in cold dark matter, were restricted to shorter distances. This difference in the travel distances of particles had a profound effect on the formation of cosmic structures. Hot dark matter would have led to the formation of large-scale structures, like superclusters, which would eventually break apart into individual galaxies. Cold dark matter, on the other hand, allowed for the formation of smaller structures, such as galaxies, which then grouped together to form clusters and superclusters. Recent observations, particularly the deep field images from the Hubble Space Telescope, show that galaxies were indeed the first structures to form in the early universe. This supports the notion that most dark matter is cold, rather than hot, and aligns with the predictions of the lambda CDM model. This is also why neutrinos, which are considered a form of hot dark matter and move nearly at the speed of light, cannot account for the majority of dark matter. The nature of dark matter is still one of the greatest mysteries in modern physics. By definition, dark matter does not interact with visible matter, such as stars and planets, except through gravity. This means that dark matter might not be composed of entirely new types of particles. In fact, it could include familiar objects like planets, brown dwarfs, red dwarfs, white dwarfs, neutron stars, and even black holes. These objects are grouped together under the category of MACOs, massive compact halo objects, and for a time, scientists believed that MACOs might constitute the majority of dark matter. However, there is now strong evidence against this idea. If MACOs were indeed the dominant form of dark matter, we would expect to see more ordinary matter scattered around the universe, particularly in regions where it could be illuminated by the light of nearby stars. Yet, observations show that we do not see this matter in the quantities that we would expect. The Big Bang theory provides another important piece of the puzzle. According to this theory, the elements we observe today were formed in the early stages of the universe. If there had been more ordinary matter, often referred to as baryonic matter, in the early universe, we would expect to see a higher abundance of light elements like helium, lithium, and other heavier elements. However, what we observe in the universe today indicates that only about 4 to 5% of the universe's total mass is made up of this regular matter. This discrepancy suggests that the majority of dark matter is not composed of ordinary matter, but must be made of something entirely different, something we have yet to fully identify. However, large-scale studies of galaxies and other cosmic structures have revealed an intriguing and puzzling fact. The total amount of matter in the universe is only about 30% of what is necessary to maintain its stability. This gap has raised crucial questions about the unseen forces shaping the cosmos. Further investigations have uncovered that only a tiny fraction of what we call dark matter appears to exist in the form of ordinary hidden objects such as small planets or black holes, which are known as MACOs, massive compact halo objects. These mysterious objects have been studied using gravitational microlensing, a technique that observes the bending of light by gravity. Despite these efforts, it has become clear that MACOs cannot account for the vast majority of dark matter. Their masses fall within a range that excludes nearly all plausible candidates for dark matter. In the search for answers, scientists have turned to the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. Missions such as WMAP, Wilkinson Microwave Anisotropy Probe, and Planck have provided compelling evidence that a staggering 85% of the universe's mass is invisible, existing in a form that interacts very little with light or ordinary matter. The only interaction we can observe is through gravity, indicating that dark matter itself is largely invisible and can only be detected through its gravitational effects on nearby galaxies and cosmic structures. Given that ordinary matter, often referred to as baryonic matter, doesn't account for most of the dark matter, it follows that dark matter must be composed of something entirely different. Specifically, it is believed to be made of non-baryonic matter. Two primary theories have emerged regarding the nature of this mysterious substance. Dark matter might be made up of exotic, as yet undiscovered particles, or it might consist of primordial black holes, dense, ancient black holes formed in the early universe. Unlike baryonic matter, which helped create the elements produced during the Big Bang through a process known as Big Bang nucleosynthesis, these non-baryonic particles are almost entirely undetectable, except for the gravitational influence they exert. Some types of dark matter are theorized to interact with each other, self-interacting dark matter, or with regular particles like weakly interacting massive particles, WIMPs. These interactions, though rare, could produce detectable signals such as gamma rays or neutrinos, particles with extremely small masses, potentially observable through indirect detection methods. The search for dark matter has led to the proposal of various candidates, each with distinct strengths and weaknesses. WIMPs, one of the most popular candidates, are elementary particles that interact through gravity and possibly other weak forces, such as the weak nuclear force. Many theoretical models suggest that WIMPs were created in the early universe in a process similar to that of regular particles. If WIMPs make up dark matter, they are classified as cold dark matter, meaning they move slowly in comparison to the speed of light. To explain the current abundance of dark matter, these particles would need to annihilate each other in specific ways, releasing energy and matter. The masses of these particles are thought to be around 100 gigaelectron volts, GeV, and their interactions would occur through the electroweak force, a fundamental force that unites the electromagnetic and weak nuclear forces. This idea is often referred to as the WIMP miracle, because it fits remarkably well with predictions from supersymmetry theories, an extension of the standard model of particle physics that suggests the existence of heavier particles beyond those already discovered. A stable supersymmetric partner particle is considered a prime candidate for dark matter. Researchers continue to hunt for WIMPs by searching for their annihilation products, such as gamma rays, neutrinos, and cosmic rays emanating from nearby galaxies. In laboratories, experiments attempt to directly detect WIMPs by measuring their interactions with atomic nuclei. Particle colliders such as the Large Hadron Collider, LHC, have also been used to try and create WIMPs. However, by the early 2010s, experiments at the LHC had failed to produce strong evidence for supersymmetry, casting doubt on the simplest WIMP models. Axions are another potential candidate for dark matter. First proposed in 1978 by physicists Frank Wilczek and Steven Weinberg, these incredibly light and weakly interacting particles were initially introduced to resolve a problem in the theory of quantum chromodynamics, QCD, the field of physics that explains how quarks and gluons interact within atomic nuclei. Axions are believed to have been produced in the early universe and could remain present today. Their abundance, depending on their mass, could provide an elegant explanation for certain small-scale mysteries in the lambda cold dark matter (LCDM) model, the dominant framework used to understand the universe's evolution. In recent years, the axion theory has gained significant traction, particularly after WIMPs were not detected. Due to their extremely low mass, axions could potentially explain some of the unresolved issues within dark matter research, especially on small scales. Another fascinating theory involves primordial black holes, hypothetical black holes that could have formed in the very early universe, right after the Big Bang, during the period of rapid expansion known as cosmic inflation. During this epoch, incredibly dense regions of subatomic matter could have collapsed under their own gravity, creating black holes without the need for a star's death, as is typically the case for regular black holes. These primordial black holes would predate the formation of the first stars and could have a wide range of masses from incredibly small, even on the scale of atoms, to far larger than typical stellar black holes. The idea of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by renowned physicist Stephen Hawking in 1971. Over time, this theory gained increasing attention as a potential explanation for dark matter. One key advantage of primordial black holes is that the theoretical framework for black holes, rooted in general relativity, was already well established, and black holes themselves had already been confirmed to exist. However, creating primordial black holes would likely require complex conditions, such as exotic forms of cosmic inflation or new theories beyond the standard model of particle physics. In 2015, the detection of gravitational waves from black hole mergers reignited interest in primordial black holes as dark matter candidates. Some of these black holes, detected through their mergers, had masses that seemed too large to have been formed by typical processes like stellar collapse, suggesting they could be primordial. However, a subsequent study that looked for signs of gravitational lensing caused by intermediate mass black holes, expected to be a significant contributor to dark matter, failed to find evidence for their existence. This raised questions about the validity of this theory, although some researchers have argued that the negative results could be attributed to assumptions about the mass range of these black holes. Despite the skepticism, the search for primordial black holes continues. Further observations, particularly from cutting-edge instruments like the James Webb Space Telescope, may offer new insights into this elusive theory. Historically, scientists believe that extremely small black holes, tiny primordial black holes, might constitute a large portion of dark matter. However, data from the Voyager 1 spacecraft, which traveled beyond the influence of the Sun and measured the flow of positrons and electrons, led to surprising results. The flow of particles was too low, and their energy levels did not match the predictions, prompting researchers to conclude that tiny black holes may be too rare to account for dark matter. Nonetheless, the idea of dense forms of dark matter remains a vibrant area of research, with new theories continuously emerging. Some even suggest that dark matter might be cooled under specific conditions. As of 2018, the mystery surrounding dark matter remains unsolved, And in 2019, further observations of the Andromeda Galaxy showed no signs of microlensing effects, which would have been expected if tiny black holes were present. This discovery cast more doubt on the existence of primordial black holes as the dominant source of dark matter. Yet the gap in our understanding persists. There exists a mass range of primordial black holes smaller than those currently detectable with optical microlensing, which could potentially make up all of dark matter. This area remains an open frontier, with researchers continuing to investigate the possibility that primordial black holes could provide the missing piece of the cosmic puzzle. If dark matter is composed of particles that interact minimally with everything else, an important question arises. Could these particles eventually form objects like planets, stars, or black holes? Historically, the answer has been no, and there are two fundamental reasons for this conclusion. Unlike regular matter, dark matter cannot easily lose energy, which is crucial for forming dense, stable objects like stars and planets. In regular matter, as particles fall inward due to gravity, they lose energy, allowing them to slow down and condense into stable, dense objects. However, dark matter does not behave in this way. Its interactions are so weak that it cannot dissipate energy in the same manner, preventing the formation of dark matter stars or planets. The mystery continues to unfold, challenging our understanding of the universe and the very nature of the matter that makes up the cosmos. Dark matter remains one of the most elusive phenomena in modern physics, a subject of intense study and speculation. However, despite decades of investigation, scientists have yet to pin down exactly what dark matter is or how it behaves. Unlike ordinary matter, which interacts with other forms of matter in a variety of ways, through gravity, electromagnetism, and nuclear forces, dark matter is largely invisible to these interactions, save for gravity. This distinct property makes it both difficult to study and crucial to our understanding of the universe's structure. At the heart of the mystery is the fact that dark matter doesn't lose energy the way regular matter does. When regular particles collide or interact, they often lose energy in forms like light, heat, or radiation. Dark matter, however, doesn't interact strongly with other matter, making it impervious to such processes. It doesn't release energy through processes like nuclear fusion, which powers stars and lights up the night sky. Instead, it appears to only interact through gravity and potentially weak forces, though even that is still speculative. This lack of interaction means that dark matter can't form dense, compact objects like stars or planets. Particles within dark matter that are pulled inward by gravitational forces simply heat up and speed up, ultimately escaping without forming such structures. If dark matter is made up of particles, these subatomic entities move through space in ways that are almost impossible to detect. They pass through every square centimeter of Earth millions, even billions of times every second. Current experiments aim to catch these particles in action, searching for traces that could reveal their existence. Among the most commonly researched candidates are WIMPs, weakly interacting massive particles, which remain a leading theory. However, axions, a hypothetical particle proposed as a solution to dark matter, have also gained traction, especially with projects such as the Axion Dark Matter Experiment, ADMX. Aside from WIMPs and axions, other exotic possibilities are being explored, including heavy particles from a hidden sector, which may only interact with regular matter via gravity. There are two primary types of experiments focused on detecting dark matter: direct detection and indirect detection. Direct detection experiments aim to spot the moment when a dark matter particle collides with an atomic nucleus. When this happens, the nucleus might release a tiny amount of energy, either as light or vibrations, which can be measured by sensitive detectors. To achieve this, the experiments must minimize interference from any background noise, which is why they're often conducted deep underground, shielded from cosmic rays and other disturbances. Notable underground laboratories include the Starwell Mine, the Sudan Mine, and the Gran Sasso National Laboratory. The technology used in these experiments includes cryogenic detectors, which measure the heat produced by particle collisions in materials like germanium, and noble liquid detectors, which track light emitted when dark matter particles hit liquids like xenon or argon. Some of the most prominent experiments in this field are CDMS, CREST, Xenon, and LUX. These detectors are designed to distinguish between dark matter and background particles, which mostly scatter off electrons. Dark matter particles, by contrast, interact with atomic nuclei, making them harder to detect but also easier to differentiate from common particles. Indirect detection experiments, on the other hand, try to observe the after effects of dark matter particles annihilating or decaying into other particles. These experiments aim to detect particles such as gamma rays, positrons, or antiprotons, which could be produced in dark matter and annihilation events. So far, no experiment has provided definitive proof of dark matter through direct detection, but each failure brings scientists closer to narrowing down what dark matter particles might look like. One fascinating observation comes from the Dharma Ni and Dharma Libra collaborations, which have noted a yearly fluctuation in their data, potentially linked to the Earth's motion through the dark matter halo surrounding the Milky Way. However, this fluctuation has not been confirmed by other experiments like LX or Super CDMS, leaving the phenomenon a mystery that could either reveal new properties of dark matter or be explained by another unknown factor. Certain experiments, particularly those with directional sensitivity, track the movement of dark matter particles. By measuring the motion of particles in relation to the solar system's orbit around the galactic center, these experiments try to separate dark matter signals from the background noise of cosmic radiation. Notable efforts in this area include the DMPC and drift experiments, which aim to detect the direction in which dark matter particles are moving. This kind of data could offer new insights into the nature of dark matter itself. The indirect detection approach also seeks to understand dark matter by looking for signs of an annihilation or decay in regions with high concentrations of dark matter. The center of the Milky Way, for example, could be a hotbed of dark matter interactions. If two dark matter particles collide, they could annihilate each other, releasing gamma rays or pairs of normal particles and their opposites, antiparticles. Alternatively, if dark matter particles are unstable, they could decay into standard particles or other exotic forms of matter, which might be detectable through the surge of gamma rays, positrons, or antiprotons emerging from dark matter-rich areas. However, the challenge lies in distinguishing signals from dark matter annihilation or decay from those produced by other cosmic phenomena. For example, many types of celestial events can emit similar radiation, meaning that a signal might come from something other than dark matter. To confirm a dark matter discovery, scientists need multiple corroborating signals from different experiments. As dark matter particles pass through celestial bodies like the Sun or Earth, they may interact with atoms and lose energy. This process could cause dark matter to accumulate at the centers of these bodies, where it might be more likely to collide and annihilate. Such events could produce high-energy neutrinos, which would serve as strong evidence of dark matter made of WIMPs. Instruments like the Amanda, IceCube, and Antares detectors are actively searching for these signals. Moreover, the detection of gravitational waves in 2015 by LIGO opened up an entirely new avenue for observing dark matter, particularly if it exists in the form of primordial black holes. Some experiments, such as the Energetic Gamma Ray Experiment Telescope, EGRET, have observed an excess of gamma rays coming from the Milky Way. In 2008, EGRET reported more gamma rays than expected, which many scientists initially attributed to errors in estimating the telescope's sensitivity. Yet, in 2009, the Fermi Gamma Ray Space Telescope observed an even more puzzling excess of gamma rays from the galactic center, which could suggest dark matter annihilation or an unknown source of high-energy emissions. Further analysis of Fermi's data in 2012 revealed a possible 130 giga-electron-volt signal, interpreted by some as a potential result of dark matter annihilation at even higher energies. Other experiments, such as the Pamela mission launched in 2006, have found an unusual surplus of positrons, which might be linked to dark matter. However, no similar excess of antiprotons was found, making it difficult to draw a direct connection between these findings and dark matter. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station detected high-energy cosmic rays in 2013 that could be related to dark matter annihilation, though no definitive link has been confirmed. In another approach, researchers are trying to create dark matter in the laboratory. At facilities like the Large Hadron Collider, LHC, proton collisions might yield dark matter particles, which could be detected indirectly by noticing large amounts of missing energy and momentum. If dark matter exists, it might not interact directly with the detectors, but the absence of energy in the system could be a telltale sign of its presence. The LE experiment also uses a similar method, investigating the interaction between dark matter and electrons, providing further constraints on its potential properties. Despite the lack of direct evidence for dark matter, alternative theories continue to be proposed. Some scientists have questioned the validity of general relativity on large cosmic scales, proposing modifications that could explain the observed gravitational effects without invoking dark matter. These theories include modified Newtonian dynamics, MON, relativistic versions of MOND, and even ideas like negative mass or entropic gravity. While some of these theories have had limited success in explaining specific observations, such as gravitational lensing tests in 2016 and measurements supporting indeed in 2020, most astrophysicists remain convinced that dark matter exists in some form. Even as dark matter remains mysterious, we continue to explore the broader cosmos, which is equally perplexing. Dark energy, a completely different yet equally puzzling force, drives the rapid expansion of the universe. Together with dark matter, dark energy accounts for approximately 95% of the total energy in the universe, with dark energy alone making up 68%. The discovery of dark matter could be a crucial step in unraveling the full story of the universe's evolution, from the smallest subatomic particles to the largest structures in the cosmos. In the grand expanse of the universe, we are surrounded by more than just the visible stars and galaxies we can observe. While ordinary, visible matter makes up only about 5% of the universe's total energy budget, something far more mysterious takes up the majority of the remaining mass energy content. Dark matter accounts for roughly 26%, while the enigmatic dark energy dominates, making up approximately 68% of the universe's total energy density. Dark energy, in particular, stands out as the dominant force driving the accelerated expansion of the cosmos. Yet its nature remains one of the most profound mysteries in modern science. The cosmic energy balance is far more complex than one might imagine. Despite their low density, around 7 times 10 to the power of negative 30 grams per cubic centimeter, neutrinos and photons barely contribute to the overall mass energy budget of the universe. Dark energy, by contrast, is evenly spread throughout space, exerting a consistent influence on the fabric of the universe. This is a critical distinction because, unlike ordinary matter or dark matter, dark energy does not clump together. Instead, it is spread uniformly across the cosmos. This subtle, omnipresent force continues to shape the fate of the universe in ways that are still not fully understood. The existence of dark energy was first suspected by scientists in the late 20th century after careful study of distant supernovae, particularly type Oye supernovae. These supernovae serve as excellent standard candles for measuring astronomical distances as they shine with a consistent brightness. By comparing their observed brightness to the redshift, the stretching of light as objects move away from us, astronomers were able to confirm that the universe's expansion was not just continuing, but accelerating. This discovery, which upended previous expectations that gravity from all matter would slow the expansion, marked a pivotal moment in cosmology. The realization that the universe's expansion was speeding up, not slowing down, reshaped our understanding of the cosmos and hinted at the presence of some invisible force working against gravity. In the years following this groundbreaking discovery, multiple lines of evidence have reinforced the idea that dark energy is not just a theoretical construct, but a fundamental feature of the universe. However, the precise nature of dark energy remains elusive. Several theories have been proposed to explain its mysterious properties. One of the leading ideas is that dark energy is a cosmological constant, a steady and unchanging form of energy that is evenly distributed throughout space. This concept was first introduced by Albert Einstein in 1917 as part of his equations of general relativity. Einstein added the cosmological constant to his equations in an attempt to explain a static, unchanging universe, an idea he later abandoned when it was discovered that the universe was actually expanding. But the cosmological constant can be thought of as a form of vacuum energy, the energy inherent in empty space itself. This energy does not get diluted as the universe expands, meaning that as space grows, the total amount of vacuum energy remains constant. Some theorists suggest that this constant energy could act as a repulsive force that caused the accelerated expansion of the universe. Einstein originally saw it as a counterbalance to gravity, preventing the universe from collapsing under its own weight. However, the discovery of the expanding universe in 1929 by Edwin Hubble made this model obsolete, leading Einstein to famously refer to his introduction of the cosmological constant as his greatest blunder. Yet, even after Einstein's rejection of the cosmological constant, the idea has not been entirely discarded. In fact, with the confirmation that the universe is not only expanding but accelerating, the cosmological constant has reemerged as a possible explanation for dark energy. Another theory suggests that dark energy could be the result of evolving scalar fields, energy sources that vary over time and space. Unlike the cosmological constant, which remains unchanged, scalar fields such as quintessence or moduli could fluctuate, potentially offering a more dynamic explanation for dark energy's role in the universe. Over the years, these ideas have been supplemented by more speculative theories. Some cosmologists have proposed that dark energy might be influenced by other forces or interactions, or even that it could be coupled with gravity in ways that we do not yet understand. One such idea is known as interacting dark energy, which posits that dark energy might interact with other components of the universe, such as dark matter, in ways we have not yet detected. These theories, while intriguing, still lack the empirical evidence needed to confirm them, leaving dark energy's true nature firmly in the realm of mystery. The cosmological constant, when incorporated into the equations of general relativity, helps explain the accelerated expansion of the universe. By adding it to the standard model of cosmology, known as the lambda cold dark matter, lambda CD model, scientists have been able to reconcile the observed acceleration with the underlying physics. This model has become the standard framework for understanding the large-scale structure of the universe, and it has been supported by a wealth of observational data, including measurements from the Planck satellite and the Supernova Legacy Survey. The lambda CDM model is particularly powerful because it aligns with a broad range of observations. For example, the discovery of irregularities in the cosmic microwave background radiation in the early 1990s helped refine our understanding of the universe's energy content. These irregularities were interpreted as small fluctuations in the density of matter in the early universe, which eventually led to the formation of galaxies and large-scale structures. More recent observations, such as the 2001 2DF Galaxy Redshift Survey and the WMAP satellite's measurements, have further confirmed the existence of dark energy and its role in shaping the cosmos. Despite these advances, there is still much we do not know about dark energy. One of the most pressing challenges in modern cosmology is measuring the equation of state for dark energy. This equation describes how the combined densities of matter, energy, and vacuum energy relate to temperature and pressure in different regions of space. By studying the equation of state, scientists hope to gain insights into the fundamental properties of dark energy, including whether it behaves like Einstein's cosmological constant or if it varies over time. The search for a deeper understanding of dark energy continues to unfold. Data from cutting-edge observatories like the Hubble Space Telescope and the upcoming James Webb Space Telescope will provide crucial clues to help scientists refine their theories. In particular, recent observations from the Hubble Space Telescope suggest that dark energy has been influencing the universe for at least 9 billion years, potentially even before the universe began accelerating in the way we observe today. Yet, even with these advancements, the true nature of dark energy remains an open question. Its smooth, evenly distributed presence throughout space, along with its extremely low mass, estimated at around 10 to the power of negative 27 kilograms per cubic meter, makes it virtually undetectable in laboratory experiments. It seems to exert its influence only through gravity, making its effects observable only on the largest cosmic scales. Still, the fact that it makes up such a large proportion of the universe's energy content, around 68%, means that its role in the expansion of the universe cannot be ignored. One leading theory links dark energy to vacuum energy, a concept rooted in quantum mechanics. According to this idea, the constant creation and annihilation of virtual particles in empty space, predicted by Heisenberg's uncertainty principle, could give rise to the observed effects of dark energy. As the universe expands, the fluctuations in vacuum energy could be contributing to the accelerated growth of the cosmos. The gravitational effects of this energy would be consistent with the predictions of the cosmological constant, further reinforcing the idea that dark energy plays a key role in the fate of the universe. In the end, despite the many advances in our understanding of dark energy, it remains one of the most profound puzzles in modern science. Its precise nature, its origins, and its ultimate fate are questions that continue to challenge cosmologists around the world. As our tools for exploring the universe continue to improve, and as we gather more data from distant galaxies, supernovae, and the cosmic microwave background, perhaps we will eventually unravel the secrets of dark energy. Until then, it remains an essential, though largely invisible force that shapes the very structure of our universe. However, there lies a monumental issue at the heart of our understanding of the cosmos. The theoretical value for vacuum energy, as predicted by quantum field theory, is astoundingly larger than what we observe in reality. This glaring discrepancy has left scientists grappling for answers, struggling to reconcile this contradiction. Yet, no matter the exact nature of dark energy, it is clear that it must possess an extraordinarily potent negative pressure to account for the accelerated expansion of the universe, a phenomenon so intricately woven into the fabric of general relativity. Negative pressure is a curious concept, one that behaves similarly to mass when it comes to its gravitational effects. Both mass and pressure are incorporated into the stress-energy tensor, a central element of Einstein's equations. This tensor dictates how matter influences the curvature of spacetime, thus governing the gravitational forces at play. In the context of the universe's expansion, it is this negative pressure that drives the acceleration. Were the universe contracting instead of expanding, this very tension would serve to slow its collapse. This effect, often referred to as gravitational repulsion, creates a force that seems to push the universe apart, counteracting the gravitational attraction that normally works to pull it together. In our current understanding of the universe, there are three fundamental components that account for everything we observe: matter, radiation, and dark energy. Matter is anything that possesses mass and substance, and it behaves in a way that as the universe expands, its energy density diminishes at a rate proportional to the cube of the expansion factor. To simplify, imagine a box filled with ordinary particles. If the box doubles in size, the energy of those particles will decrease by a factor of 8, as the particles are now spread across a much larger volume. This occurs because the box is expanding in 3 dimensions, and the energy density thus becomes less concentrated. Radiation, such as light or heat, behaves differently. As the universe stretches, its energy density decreases even more rapidly than that of matter. This is due to 2 factors. Not only does the radiation spread out across a larger space, but it also undergoes a stretching of its wavelength, a phenomenon known as redshift. As the universe expands, the wavelengths of radiation become longer, leading to a loss of energy more pronounced than that experienced by matter. Then there is dark energy. Unlike both matter and radiation, dark energy is not influenced by the expansion of space. It is an intrinsic property of the fabric of space itself. No matter how much the universe stretches, dark energy remains constant, its energy density unaffected by the growing space. This enduring constancy sets dark energy apart, marking it as the mysterious force that drives the ongoing acceleration of the universe's expansion. The evidence for dark energy, though indirect, comes from a variety of sources that collectively help us piece together its elusive nature. One of the strongest indicators comes from distance and redshift measurements. By examining how the distance to objects correlates with the stretching of their light, scientists have discovered that the universe has been expanding at an increasingly rapid rate in its later stages. This acceleration hints at an unknown force at work, a force which is likely dark energy. Furthermore, the universe's flatness, the observation that it does not exhibit any detectable curvature, suggests the presence of energy beyond that of normal matter or dark matter. This additional energy, theorized to be dark energy, helps to explain the flatness of the universe. Large-scale cosmic density waves, visible through the arrangement of galaxies, also provide clues that point toward dark energy. These patterns help refine our understanding of how the universe expands and the mysterious force behind it. In 1998, a team of astronomers known as the High Z Supernova Search Team made a groundbreaking discovery by studying Type 1a supernova, exploding stars. They observed something entirely unexpected. The universe's expansion was not slowing down, as previously assumed, but instead speeding up. Another group, the Supernova Cosmology Project, came to the same conclusion in 1999, earning them the Nobel Prize in Physics in 2011. These observations have since been reinforced by additional data from various sources, such as the cosmic microwave background radiation left over from the Big Bang, the bending of light by gravity, gravitational lensing, and the overall structure of the universe. All of this evidence fits neatly with the predictions of the lambda cold dark matter, lambda CDM model of cosmology, which incorporates dark energy as a critical element. Some critics, however, argue that only the redshift and distance measurements offer robust evidence for dark energy. They claim that other findings, such as the cosmic microwave background radiation, provide only indirect support. But even these patterns, as observed in the cosmic microwave background, suggest distances larger than would be expected in a universe without dark energy. Supernovae play a vital role in studying the expansion of the universe, acting as standard candles. Their predictable brightness allows astronomers to measure their distance and, by comparing this with their redshift, gauge the speed at which the universe is expanding. Type Ia supernovae are especially valuable because of their consistent and well-understood luminosity, making them some of the most reliable markers in cosmic measurements. Recent data indicate that dark energy constitutes approximately 71.3% of the universe's total energy content. The remaining portion is accounted for by dark matter and regular matter. The lambda CDM model, which describes how galaxies, stars, and other cosmic structures form, also aligns with the notion that regular matter comprises only 30% of the universe's critical density, the amount needed for the universe to be geometrically flat. In 2011, the Wigglesy Galaxy Survey, which studied over 200,000 galaxies, provided additional evidence for dark energy. By measuring the distances to galaxies up to 2 billion parsecs away, the team confirmed that the expansion of the universe had been accelerating over time, reinforcing the concept of cosmic acceleration. For the universe to remain flat, as observations suggest, there must be an additional form of energy. Since the visible matter, baryonic and dark, only accounts for about 30% of the required energy, the rest, approximately 70%, must be something like dark energy. Data from the Wilkinson Microwave Anisotropy Probe, WMAP, in the early 2000s indicated that around 8% of the universe is composed of dark energy. More recent observations from the Planck spacecraft revised this figure to approximately 68.3% dark energy, with dark matter comprising 26.8% and ordinary matter making up just 4.9%. Dark energy also explains certain anomalies observed in the cosmic microwave background. When photons, light particles, pass through regions of intense gravity, such as galaxy clusters or voids, the empty spaces between clusters, they lose energy, creating cold and hot spots in the background radiation. This phenomenon, known as the integrated Sachs-Wolf (ISW) effect, is another critical piece of the puzzle pointing toward the existence of dark energy. In more recent times, scientists have begun using the Hubble constant, a key measure that tracks the expansion of the universe over time, to estimate dark energy's influence. By studying galaxies that have passively evolved, those that no longer form new stars, scientists can act like cosmic timekeepers. By measuring the age of these galaxies and their redshift, they can directly assess the rate at which the universe has expanded throughout history. Despite the wealth of evidence, dark energy remains one of the most perplexing mysteries in modern physics. While it is widely accepted as the force responsible for the universe's accelerated expansion, the precise nature of dark energy remains unknown. This has led researchers to approach the problem from multiple directions. Some are revisiting Einstein's theory of gravity to see if there is something we have missed in our understanding of space-time. Others are investigating the fundamental properties of dark energy itself, and some are exploring alternative explanations based on observational data. One of the simplest and most widely accepted ideas is that dark energy is a fundamental property of space itself. In this view, empty space is not truly devoid of energy, but rather contains what is known as vacuum energy. This concept, referred to as the cosmological constant, denoted by the Greek letter lambda, is a key component of the lambda CDM model, the most widely accepted model of the universe's structure and evolution. Since mass and energy are linked by Einstein's famous equation, E=squared, this vacuum energy should also exert a gravitational influence, helping shape the expansion of the universe as we know it. The universe, as we know it, is a vast and perplexing entity, and one of the greatest challenges in modern physics lies in understanding the nature of dark energy and its impact on cosmic evolution. For decades, scientists have grappled with a fundamental paradox. Quantum physics predicts that the amount of vacuum energy in space should be staggeringly large, by about 120 orders of magnitude, yet we observe something vastly different. If this theoretical vacuum energy were indeed as immense as predicted, the universe would have expanded at an incredibly violent rate in the early moments after the Big Bang. Such an explosive expansion would have made it impossible for galaxies, stars, or even planets to form. So what accounts for the delicate balance that allowed the universe to evolve in a way that made life as we know it possible? The key must lie in the cancellation of most of this excess vacuum energy, but it's clear that whatever this mysterious force is, it does not eliminate the energy entirely. Something is holding this enormous potential energy in check, but the exact nature of that something remains elusive. In recent years, one hypothesis has gained traction among some physicists. Dark energy might not be the constant force it was once believed to be. Instead, it could be an evolving, changing energy field, a concept referred to as quintessence. Unlike the cosmological constant, which is uniform and unchanged across space and time, quintessence suggests a dynamic energy field that fills the universe, varying in strength as it influences the expansion of the cosmos in different ways. For quintessence to function, however, the energy field must be extremely light, almost ethereal, so it does not clump together like ordinary matter. This theory could account for some of the strange behaviors of the universe, such as its current rate of expansion. Interestingly, some versions of quintessence predict that the universe's expansion should be slightly slower than what would be expected if dark energy were a fixed, unchanging quantity. However, despite this promising theoretical framework, there has been no conclusive evidence to confirm or disprove quintessence, leaving this idea a tantalizing yet speculative possibility. Another compelling mystery lies in the timing of the dominance of dark energy. Why did it begin to dominate the universe's expansion when it did, about 5 billion years ago? If dark energy had taken over too early, galaxies might not have formed, and life would never have had the opportunity to emerge. Some scientists argue that this could simply be a coincidence, just the natural course of events in an ever-changing cosmos. However, others see it as evidence for the anthropic principle, the idea that the universe must be the way it is, because we are here to observe it. Some models of quintessence even propose a tracker mechanism, which might explain why dark energy's effects became noticeable at this specific moment in the universe's history. These models tie dark energy's behavior to the density of radiation in the early universe, offering a potential explanation for its sudden prominence. In more extreme versions of quintessence, however, things take an even stranger turn. One possibility, dubbed phantom energy, suggests that dark energy might not only remain constant, it could grow stronger over time. If this is true, the universe would not simply continue expanding at an accelerated rate, but the expansion would eventually reach a point where it becomes so violent that the universe would tear itself apart in a catastrophic event known as the Big Rip. In this horrific scenario, galaxies, stars, planets, and even atoms themselves would be torn asunder as the force of expansion exceeds everything in its path. Another bizarre possibility comes from a theory called K-essence, which posits the existence of exotic forms of energy that behave in ways completely different from anything we've observed in ordinary matter. Some versions of K-essence even propose the existence of negative kinetic energy, which could lead to unpredictable effects on the very structure of the universe itself. Recent astronomical observations have brought further complexity to our understanding. A growing inconsistency, known as the Hubble tension, involves discrepancies in the measured rate of the universe's expansion. Some researchers believe that this tension could provide a clue that only certain quintessence models, those that involve additional interactions, are viable. Yet despite the wild and varied theories, dark energy remains one of the most profound mysteries in modern physics. At the core of this enigma lies Einstein's theory of general relativity, which has long served as the foundation for our understanding of gravity and the behavior of space-time. Some scientists have speculated that if general relativity could be modified or extended in certain ways, we might not even need to invoke the concept of dark energy to explain the universe's accelerating expansion. Numerous alternative theories have been proposed over the years, all attempting to explain the universe's behavior without relying on dark energy. But so far, none of these theories have been fully proven or widely accepted. In fact, a key observation, the detection of gravitational waves from the event GW70817, has already ruled out many of these alternative explanations, suggesting that they cannot account for the universe's observed expansion. Despite these challenges, the vast majority of physicists remain steadfast in their belief that dark energy is a real and fundamental aspect of the cosmos. Competing ideas simply fail to match the wealth of observational data as precisely as the standard model of dark energy does. Scientists estimate that the expansion of the universe began to accelerate around 5 billion years ago. Prior to this, the gravitational pull of matter, both ordinary and dark, had been slowing down the universe's expansion. But as the universe grew in size, dark matter gradually spread out, and its influence waned, while dark energy remained nearly constant. Over time, dark energy's influence grew stronger, eventually dominating the universe's expansion, causing it to speed up at an accelerating rate. One of the most fascinating aspects of dark energy is its persistence. While dark matter's density decreases as the universe expands, dark energy remains almost unchanged. For every time the universe doubles in size, the amount of dark matter per unit of space is halved, but the amount of dark energy remains essentially constant. Looking to the future, the fate of the universe hinges on the true nature of dark energy. If dark energy remains constant, as is predicted by the cosmological constant model, the universe will continue expanding indefinitely. In this scenario, galaxies outside our local group will drift further away from us, moving faster and faster until they surpass the speed of light. Not in violation of the laws of relativity, but because space itself is expanding. As galaxies reach the cosmic event horizon, an estimated 16 billion light-years away, the light they emit will be stretched to increasingly longer wavelengths, eventually becoming invisible to us. Beyond this point, any signals from distant galaxies will be forever unreachable, and the universe will appear empty, with only our local group of galaxies remaining visible. Over the course of trillions of years, even this local group will eventually reach a state of heat death, in which all energy is evenly distributed and no meaningful work can be done, much like the fate once predicted for a matter-dominated universe before the discovery of cosmic acceleration. However, this seemingly inevitable fate is not the only possibility for the future. Other theories, like the one proposing phantom energy, suggest that dark energy could continue to grow stronger, eventually leading to the catastrophic Big Rip, where the universe's expansion becomes so extreme that it rips apart galaxies, stars, planets, and even atoms. Alternatively, dark energy might change over time, potentially reversing its effects and leading to a big crunch, where the expansion of the universe halts and reverses, pulling everything back into a singularity. There is even the possibility that dark energy follows a cyclical pattern, causing the universe to expand, collapse, and then begin again in an eternal cycle of big bangs and big crunches. While none of these more dramatic theories have been confirmed, they remain intriguing possibilities as scientists continue their research. The true nature of dark energy and its ultimate role in determining the fate of the universe remains one of the greatest unsolved mysteries in cosmology. The story of the universe's past, present, and future, from the earliest moments of the Big Bang to the farthest reaches of time, is a tale still being written. Early in the universe's history, during the first trillionth of a second, the laws of physics as we know them may not have applied. This period, known as the Planck epoch, saw the emergence of the four fundamental forces that govern the universe today: gravity, electromagnetism, the weak force, and the strong force. It was during this time that cosmic inflation took place, causing the universe to expand at an unimaginable rate. Tiny fluctuations during this rapid expansion are believed to have seeded the formation of the structures we see today, like galaxies. While we've learned a great deal about the early stages of the universe, there is still much that remains a mystery. We don't yet have the tools to directly test some of the ideas from particle physics that could help us understand the very first moments of the cosmos. The journey to unraveling these mysteries is ongoing, and with each discovery, we inch closer to understanding the true nature of the universe itself. However, by applying well-established physical laws to extremely high temperatures, scientists are able to make educated guesses about what happened during the first moments after the Big Bang. While we cannot directly observe the very beginnings of the universe, we can piece together a narrative by tracing back the timeline and observing the marks it has left in the cosmos. For the first 380,000 years after the Big Bang, the universe underwent dramatic, almost incomprehensible transformations, events so extreme that they shaped the very structure of everything we know today. In the earliest moments, subatomic particles formed in stages, coming together in a chaotic and violent dance. At this time, the universe was filled with nearly equal amounts of matter and antimatter. However, this delicate balance didn't last long. Matter and antimatter annihilated each other in a massive explosion of energy, leaving behind only a small fraction of matter. This minuscule amount of leftover matter became the seeds of everything that would later form: stars, galaxies, planets, and eventually life itself. By the time 1 second had passed after the Big Bang, neutrinos, tiny particles that hardly interact with anything, split off from other particles, creating what is known today as the cosmic neutrino background. If primordial black holes existed, they would have formed around this time as well. Just 2 minutes after the Big Bang, protons and neutrons began to clump together, forming more complex subatomic particles. At this crucial moment, conditions were right for nuclear fusion, a process that allowed the first elements to emerge. Approximately 25% of the protons and all of the neutrons fused into heavier elements, starting with deuterium, which quickly transformed into helium-4. By 20 minutes after the Big Bang, the universe was no longer hot enough for nuclear fusion to continue, but it was still far too hot for atoms to form, and light could not travel freely. At this point, the universe had become a dense, opaque plasma. Around 18,000 years later, as the universe began to cool, electrons combined with helium nuclei, marking the start of a new epoch in cosmic history, the recombination epoch. By 47,000 years after the Big Bang, matter began to dominate over radiation. As the universe cooled further, neutral helium atoms formed, and by the time it reached 100,000 years, helium hydride was the first molecule to appear. Later, hydrogen and helium hydride combined to form molecular hydrogen, which would serve as the fuel for the first stars. Then, around 370,000 years after the Big Bang, neutral hydrogen atoms fully formed, and the universe entered a new phase known as recombination. This event marked the point where photons, particles of light, were no longer scattered by free electrons. For the first time, light was able to travel freely through the universe, unimpeded. These ancient photons, relics of the universe's infancy, can still be detected today as the cosmic microwave background, CMB, the oldest light we can observe. From roughly 380,000 years to about 1 billion years after the Big Bang, matter began to clump together, drawn into pockets by the gravitational pull of dark matter. Slowly, clouds of hydrogen gas collapsed under their own weight, forming the first stars and galaxies. This period, known as the Cosmic Dark Ages, was a time of profound silence and darkness. Very few sources of light existed, with most of the photons in the universe being relics from the decoupling process. These photons, along with the 21-centimeter radio emissions from hydrogen atoms, served as the only sources of light during this time. The universe remained mostly dark until the first stars ignited, around 200 million to 500 million years after the Big Bang. The formation of the first stars and galaxies is still a subject of intense study. Though we haven't yet observed these earliest stars directly, theories suggest that they were massive, likely weighing between 100 and 300 times the mass of our Sun. These stars were composed mainly of hydrogen and helium, with little to no heavier elements. Their sheer mass caused them to burn through their fuel rapidly, living only a few million years before exploding in a powerful event known as a pair instability supernova. These early supernovae scattered the basic elements, such as carbon and oxygen, throughout the universe, enriching it with the building blocks of life. Around 250 to 500 million years after the Big Bang, galaxies began to cluster together, forming large structures known as galaxy clusters and superclusters. The high-energy radiation from the first stars, along with small galaxies and quasars, triggered a process known as reionization. This event gradually took place over a period lasting until about 1 billion years after the Big Bang. While the precise timing is still under investigation, reionization marked the end of the universe's dark ages. The universe was no longer a dense and quiet place. It had become a much more energetic and active environment, with galaxies beginning to form and evolve in a way more similar to what we observe today. By the time the universe reached 1 billion years of age, it had started to resemble the cosmos we see now, though it was much hotter and more dynamic. The early galaxies were smaller, and star formation was occurring at a much higher rate. Over time, galaxies shifted from being primarily large, elliptical shapes to a mix of smaller, unbarred spirals and irregular shapes. The first galaxies that scientists have observed date back to about 330 million years after the Big Bang, or roughly 13.4 billion years ago. These early galaxies were metal-poor, meaning they contained few elements heavier than hydrogen, and they were surrounded by clouds of neutral hydrogen gas, as expected. From around 1 billion years after the Big Bang, the universe began to resemble the one we see today, with galaxies shifting and evolving into the diverse forms we recognize. Since then, the universe has continued to expand and evolve, and it is expected to do so for many billions of years to come. Our Milky Way galaxy, for example, began to form its thin disk about 5 billion years ago, and our own solar system formed about 9.2 billion years after the Big Bang. However, life on Earth didn't emerge until much later, roughly 10 billion years after the Big Bang. As the universe aged, matter began to thin out, which slowed the ability of gravity to pull everything back together. At the same time, a mysterious force known as dark energy began to take hold, causing the expansion of the universe to accelerate. This shift occurred around 5 or 6 billion years ago, marking the beginning of an era dominated by dark energy, which is responsible for the universe's accelerated expansion. This phase continues today, and the universe's expansion is speeding up rather than slowing down. While our understanding of the universe is robust, there are still many mysteries surrounding its distant future. In roughly 100 billion years, about 86 billion years from now, the stelliferous era, the time when stars are born, will come to an end. After this, stars will no longer be born, and the universe will enter a new, much darker phase. As it continues to expand, we will only be able to observe galaxies that are relatively close to us, and eventually, all stars will burn out, leaving the universe in a state of cold, dark isolation. The ultimate fate of the universe is still a subject of intense debate, with several possible scenarios to consider. As we learn more about the current state of the cosmos, we may gain insight into the future of the universe. The discovery of the universe's expansion led to the development of the Big Bang theory. which suggests that the universe started from a state of extreme temperature and density. The lambda cold dark matter, LCDM model, a refined version of this theory, aligns well with a wide range of observations. However, as we trace the expansion of the universe backward in time to even higher temperatures and densities, we reach a point where our current physical models break down. This is where things get tricky. Approaching infinite temperature or a scale factor of 0, the moment the universe began, our physical models no longer provide accurate predictions. At this stage, theorizing about an initial gravitational singularity doesn't make sense because it falls outside the realm of our current understanding of physics. The standard model of cosmology tells us that the universe has been expanding since its very hot origins. But as we move closer to the Planck length, the smallest possible unit of space, our models fail to hold up. Below this scale, the laws of physics as we know them cease to apply, and quantum effects take over, overriding Einstein's equations of gravity. This marks the beginning of the Big Bang, though the true nature of that event remains shrouded in mystery. Following the Planck era, some theorists speculate that the universe could be modeled by extensions of the standard model of particle physics, such as grand unified theories, GUTS, which attempt to explain the fundamental forces of nature in a unified framework. But until new breakthroughs occur, the universe's very beginning and its ultimate fate remain two of the most profound mysteries in science. The quest to understand the origins and early development of the universe has led scientists to a remarkable period in cosmic history, an era so elusive and distant that it is almost beyond the reach of current observation. Still, as modern technology advances, astronomers and physicists have been able to glimpse the deepest secrets of the cosmos. However, despite all the groundbreaking discoveries, no one has yet been able to replicate or fully explain the results of these observations with absolute certainty. In particular, one of the most elusive and enigmatic periods remains the Grand Unification epoch, a phase that stretches across an unfathomably brief but critical moment of time. This period falls within the range of time between zeptoseconds and rontoseconds, extremely short spans that are nearly impossible to comprehend in human terms. The exact nature of this epoch remains speculative, as much of it exists in the realm of theory. During the time before the Grand Unification, the universe existed in a state of such extreme conditions that temperatures soared to levels unimaginable to the human mind. These temperatures, reaching quadrillions of giga-electron volts, were far beyond anything we could recreate in modern laboratories. As the universe expanded and began to cool, it might have passed through an incredible transformation, akin to how gases condense into liquids or freeze into solids, a phenomenon that could explain the vast amount of matter compared to antimatter in the universe today. The Grand Unification epoch itself, though still uncertain in its full scope and nature, is speculated to have been followed by several key phases that are supported by theoretical models. These include the electroweak and quark-hadron phases, two critical moments in cosmic evolution that have been successfully predicted by certain models and simulations. For instance, the electroweak epoch, a phase in which two of the four fundamental forces, electromagnetism and the weak nuclear force, began to merge, is considered to have been one of the most pivotal moments in the early history of the universe. In terms of its relationship with other events, the electroweak epoch is believed to have occurred either before or after the infamous inflationary epoch, and some models even suggest the two could have overlapped. Under one prominent theory, it began around rontoseconds after the Big Bang, marking the universe's explosive expansion. At this stage, the universe is believed to have grown by an astonishing factor, at least sextillion times its original size. Imagine for a moment a nanometer, about the width of a DNA molecule, expanding to a length of over 10.6 light years, or approximately 100 trillion kilometers, all in the blink of an eye. This process, known as cosmic inflation, stands as one of the most dramatic events in the universe's development, reshaping everything that would follow. However, despite the vast strides made in understanding this period, the exact mechanism behind inflation remains a mystery. While multiple theories have been proposed, one popular idea suggests that inflation began when two fundamental forces, the strong nuclear force and the electro-weak interaction, separated, effectively ending the grand unification epoch. At that point, a special field known as the inflaton field began to emerge. As this field spread and settled into its lowest energy state, it created a repulsive force that accelerated the universe's rapid expansion. Theories about inflation help to explain many of the unusual features we see in the universe today, from the large-scale structure of galaxies to the apparent uniformity of the cosmos. The concept of inflation provides a potential solution to a puzzling question. How did the universe, which began as an incredibly uniform and evenly distributed space, come to form the galaxies and clusters of galaxies we observe now? In this theory, the small fluctuations that occurred during the early stages of inflation were stretched across vast distances, eventually leading to the clumps of matter and radiation that would form the structures we see today. While the precise timing of the end of inflation remains uncertain, it is believed to have ceased sometime between 10 to the power of minus 33 seconds and 10 to the power of minus 32 seconds after the Big Bang. At this point, the universe's expansion slowed dramatically, and the particles left over from the grand unification epoch were scattered across vast distances. When inflation ended, the universe underwent a process known as reheating, during which the inflaton field released a tremendous amount of energy. This event marked the creation of a hot and dense mixture of particles, including quarks, antiquarks, and gluons. Some theories suggest that the reheating phase led directly into the electro-weak epoch, although alternative models, such as warm inflation, do not include this distinct reheating phase at all. What followed was a slower phase of expansion, but this did not last forever. Around 4 billion years ago, the expansion of the universe began to speed up once more, likely due to the emergence of dark energy, a mysterious force that began to dominate the cosmos. To this day, the universe continues to expand at an accelerating rate, propelled by this enigmatic energy. Following inflation, the universe entered a phase characterized by a superheated plasma composed of quarks and gluons, remnants of the reheating process. It was during this time that scientists first began to piece together a clearer understanding of the universe's early conditions, as the quark epoch is something that can be recreated in particle physics experiments. This epoch, which lasted until the universe was about 10 to the power of minus 12 seconds old, was defined by extreme heat and pressure, which prevented quarks from combining into larger particles. Over time, the particles created during inflation underwent a process known as thermalization, wherein they interacted with each other, reaching a state of thermal equilibrium. This process took place just prior to a major event, the electroweak symmetry breaking, which occurred approximately 10 to 15 seconds after the Big Bang, when the temperature of the universe had cooled to around 1.5 billion degrees. During this stage, the electromagnetic and weak forces had not yet split apart, and the particles involved had yet to acquire mass through the Higgs mechanism. Electroweak symmetry breaking represented a monumental shift. It marked the end of an era in which all four fundamental forces were unified and massless. Following this event, particles like the W and Z bosons, which mediate the weak force, gained mass and were no longer able to interact over the vast distances they once could. The photon responsible for the electromagnetic force remained massless and continued to operate across long distances. This transformation was crucial, as it allowed the fundamental forces to assume the forms we recognize today. With this shift, the universe entered its final phase before the formation of stable atomic structures. However, despite the universe's cooling, it was still too hot for protons, neutrons, and other fundamental particles to form stable structures. This was a time when only the most basic of particles existed in an unstable, chaotic state. It wasn't until the universe was about 10 to the power of minus 5 seconds old that the temperature had decreased enough for quarks to combine into baryons like protons and neutrons. At this stage, an intriguing event occurred. For every baryon that formed, an equal number of antibaryons should have been created as well, though the mystery of why matter ultimately dominated antimatter remains unresolved. This early stage of the universe, known as the quark epoch, was defined by intense energy and constant particle interactions. As the universe continued to evolve, more complex structures would form, eventually giving rise to the atoms, stars, and galaxies we observe today. In the vast expanse of the cosmos, a mysterious imbalance persists, a disparity that has baffled scientists for decades. The universe, as we know it, is filled with matter. Yet when we look deeper, we find that there is a curious and perplexing excess of baryons, the building blocks of matter, and a corresponding scarcity of their counterparts, the antibaryons. While this imbalance is a striking feature of the universe today, it's also one of the greatest unsolved puzzles in modern cosmology. Scientists remain uncertain as to how this asymmetry came about. To even begin to understand the origin of this cosmic discrepancy, any explanation must account for the fundamental process of baryogenesis, which occurred after the universe's incredibly rapid inflationary period, an epoch of astonishing expansion and cooling. It's here that some of the most mind-bending theories of the universe's origins begin to take shape. Yet, even with these theories in place, the observed imbalance between baryons and antibaryons seems too significant to be fully explained by the mechanisms proposed. One of the most prominent theories suggests that shortly after the Big Bang, the ratio of protons to neutrons was roughly 6 protons for every 1 neutron. However, as the universe expanded and cooled, neutrons began to decay at a rate that shifted this balance. Eventually, the ratio of neutrons to protons dropped to approximately 1 neutron for every 7 protons. This shift plays a pivotal role in the formation of elements in the early universe, and it is supported by evidence of nuclear fusion processes. This fusion, which began in the first few minutes of the universe's existence, produced light elements such as deuterium, helium, and other isotopes, elements that we can still observe in the universe today. This 1:7 ratio of hadrons, the combination of protons and neutrons, directly correlates with the proportion of elements we observe today, both in the early and current universe. About 1 second after the Big Bang, a significant event occurred. Neutrinos, subatomic particles that interact very weakly with matter, decoupled from the hot, dense environment of the early universe. These neutrinos, which have been traveling freely through space ever since, remain an enigmatic relic of the early universe, similar to the cosmic microwave background, CMB, radiation that we observe today. However, the neutrinos we are referring to here, the ones released during this brief moment after the Big Bang, possess extremely low energy, making them incredibly difficult to detect. As such, the background of cosmic neutrinos, referred to as the cosmic neutrino background CNB, may remain elusive to our detection for years, perhaps even forever. Despite the challenges in directly observing these neutrinos, Big Bang cosmology predicts their existence with remarkable precision. Indirect evidence supporting their presence comes from 2 key areas. First, the production of helium during Big Bang nucleosynthesis, and second, the irregularities seen in the cosmic microwave background. One intriguing prediction is that these cosmic neutrinos would have left a subtle imprint on the CMB. In 2015, a groundbreaking discovery occurred. Scientists detected these shifts in the CMB. The patterns they observed matched the temperature fluctuations expected from neutrinos, as predicted by the Big Bang theory. Furthermore, these shifts corresponded to the presence of exactly 3 types of neutrinos, which aligns perfectly with the 3 flavors anticipated by the standard model of particle physics. Meanwhile, another fascinating aspect of the early universe is the existence of primordial black holes, speculative objects proposed in 1966 that could have formed during the radiation-dominated era of the universe. If small irregularities in the density of matter existed, they could have been enough to trigger the collapse of certain regions under their own gravity, leading to the formation of black holes. In the midst of this chaotic process, most of the hadrons, protons, and neutrons would have annihilated with their antiparticles, leaving behind leptons like electrons, muons, and neutrinos, as well as antileptons. This annihilation process played a crucial role in the universe's evolution. As the universe cooled and expanded, the temperature dropped to a point where the formation of leptons and antileptons ceased. However, a small fraction of leptons survived, contributing to the mass of the universe. This leftover matter, which survived the destructive annihilation events, played a critical role in the universe's eventual structure. By the end of the lepton epoch, most leptons and antileptons had been wiped out, and the energy of the universe primarily existed in the form of high-energy photons, particles of light. These photons became the dominant form of energy in the universe for the next 370,000 years, constantly interacting with charged particles such as electrons, protons, and eventually atomic nuclei. Around 2 to 20 minutes after the Big Bang, the temperature had decreased enough to allow nuclear fusion to take place. In this crucial period, a mixture of neutrons and protons began fusing together, forming the earliest elements. The most prominent of these was deuterium, a hydrogen isotope, followed by helium isotopes such as helium-3 and helium-4. This fusion process continued, albeit briefly, until the temperature dropped too low for further fusion to occur. While some other heavier elements like lithium and beryllium were created, they existed in only trace amounts and were highly unstable. The exact ratios of elements created during this time depended on various factors: reaction rates, temperature, and the density of particles present. These elements, particularly deuterium, are key pieces of evidence that support the Big Bang theory. Scientists have been able to estimate the amount of each light element present in the early universe by studying ancient galaxies. The observed amounts match remarkably well with predictions made by the theory, especially the 25% helium-4 that was created from the fusion of protons and neutrons. This is much more than could be explained by stars alone, reinforcing the Big Bang model. For example, the amount of deuterium produced and its subsequent fusion into helium provides strong evidence in favor of the Big Bang. Any alternative theory of the universe's origins would need to explain not only the formation of deuterium, but also why some of it remained unfused. The exact proportions of light elements and their isotopes, especially with the small discrepancies observed in isotopes like lithium-7, further bolster the case for the Big Bang. During much of the universe's early history, its large-scale behavior was dominated by radiation, photons and neutrinos, particles that traveled near the speed of light. However, as the universe continued to cool around 47,000 years after the Big Bang, matter began to take over. The density of matter, primarily in the form of atomic nuclei, eventually surpassed that of radiation, marking a critical shift in the universe's evolution. This change in dominance allowed for the formation of small structures, as gravitational attraction could now overcome the pressure from radiation. By this point, according to the lambda-CDM model, the universe's matter consisted largely of cold dark matter, about 84.5%, with the remaining 15.5% made up of ordinary matter. The existence of dark matter is supported by compelling evidence, as it plays a dominant role in the formation and structure of the universe. In summary, the early universe was a highly dynamic and complex place, with processes of nuclear fusion, particle interactions, and cosmic cooling shaping its evolution. As we continue to explore and understand these processes, each discovery uncovers more about the fundamental nature of the cosmos and the mysterious forces that govern its existence. However, despite decades of research, scientists still don't fully understand what dark matter is. This uncertainty has left a gap in the Big Bang theory, preventing it from offering a complete explanation of how dark matter formed in the early universe. What we do know is that dark matter plays a crucial role in the development of the universe's structure, and its influence will continue for billions of years into the future. In the earliest stages of the universe, dark matter began to clump together, pulled by the force of gravity. This process occurred at an astonishing pace, much faster than the aggregation of ordinary matter. The reason dark matter clumps so quickly is that it does not interact with radiation in the same way regular matter does. Unlike normal particles, which can absorb and emit radiation, dark matter remains largely unaffected by it. As dark matter began to coalesce, it amplified small irregularities in the universe's density, tiny fluctuations left behind by cosmic inflation, which occurred in the first fraction of a second after the Big Bang. Over time, areas of the universe that were slightly denser grew even denser, while regions with fewer particles became emptier. These concentrations of dark matter were instrumental in bringing regular matter together faster than it would have on its own. One of the key reasons for the rapid clumping of dark matter is its inability to lose energy through radiation. For regular matter, in contrast, the loss of energy through radiation is what allows particles to collapse and form denser structures such as stars and planets. Dark matter, however, cannot radiate energy in this way. Instead of forming compact objects, dark matter formed vast, thin filaments and halos that spanned immense distances. Regular matter, on the other hand, could lose energy by emitting radiation, enabling it to condense into denser objects like stars and gas clouds. Around 370,000 years after the Big Bang, two monumental events occurred: recombination and photon decoupling. Recombination refers to the process in which ionized particles such as electrons and protons combine to form the first neutral atoms. Photon decoupling occurred when photons, previously trapped by interactions with these charged particles, were freed as the newly formed atoms reached stable energy states. Before recombination, the universe was extremely hot and filled with an ionized plasma. The photons kept interacting with the charged particles, preventing them from traveling freely. The universe at that time was essentially opaque, like a fog. Light existed, but it was impossible to see through. As the universe began to cool, around 18,000 years after the Big Bang, electrons started to combine with helium nuclei, forming neutral helium atoms. Neutral helium began to form at about 100,000 years, and hydrogen atoms followed about 160,000 years later. This process, known as recombination, was a groundbreaking moment in the universe's history. The name recombination can be misleading, as this was, in fact, the first time that electrons and nuclei combined in this way. Around 100,000 years after recombination, the universe had cooled enough for the formation of the first molecule, helium hydride. This molecule represented a breakthrough in molecular chemistry, and in April 2019, scientists confirmed its existence in space, specifically in the planetary nebula NGC 7027. Over time, helium hydride would interact with atomic hydrogen, leading to the formation of molecular hydrogen, the key ingredient for star formation. Hydrogen atoms, when they combine in a low-energy state, are not very efficient. Instead, they usually come together while still holding on to their high-energy electrons. After the atoms combine, these electrons rapidly release energy, transitioning to lower-energy states and emitting photons in the process. This release of photons is known as photon decoupling. Some of these photons were caught by other hydrogen atoms, but most remained free. As recombination reached its conclusion, the majority of protons in the universe had combined with electrons to form neutral hydrogen atoms. This shift from charged to neutral particles allowed photons to travel freely without being captured by other particles. For the first time, the universe became transparent to light, radio waves, and other types of electromagnetic radiation. The photons released by these neutral hydrogen atoms had a temperature of around 4,000 K, which would have appeared as a soft white light with a pale yellow or orange tint. As the universe expanded over billions of years, these photons stretched out, shifting from visible light to longer wavelength radio waves. This transformation, known as redshifting, occurs because the universe's expansion causes the wavelengths of photons to lengthen, which in turn lowers their frequencies. These redshifted photons, now in the microwave range with a temperature of about 2.7 K, can still be detected today as the cosmic microwave background, CMB. This radiation serves as a crucial source of information about the early universe and its development. Around the same time as recombination, pressure waves were already present in the electron-baryon plasma. These waves became locked into the distribution of matter as it began to condense, and were subsequently captured in the cosmic microwave background. Known as baryon acoustic oscillations, these pressure waves left behind a subtle pattern in the large-scale structure of the universe. The CMB captures a snapshot of the universe at this point, providing us with a glimpse of tiny fluctuations from the early moments of inflation. In the billions of years that followed, galaxies began to spread out, reflecting the expansion and growth of the universe over time. Yet, even after recombination and photon decoupling, the universe remained too cool for stars and galaxies to form. The process that led to the emergence of stars and galaxies began when gravity caused dense regions of gas to collapse. This took hundreds of millions of years. It was this long wait, known as the Dark Ages, that explains why stars didn't appear until much later. The Dark Ages began around 370,000 years after the Big Bang, and during this time, the universe cooled from about 4,000 K to just 60 K. For the majority of the Dark Ages, the universe was completely dark, except for the photons released during recombination, which we still detect as the CMB, and a faint glow from neutral hydrogen atoms, known as the 21-centimeter spin line. The 21-centimeter line falls within the microwave frequency range and provided the only source of light during this time. Within just 3 million years, the CMB photons had shifted from visible light into the infrared spectrum. After that, for a long time, there was no visible light in the universe, making it a truly dark place, aside from a few rare anomalies. The end of the Dark Ages came when the first stars, known as population 3 stars, began to form just a few 100 million years after the Big Bang. These early stars were the first to shine with visible light, marking a significant milestone in the universe's history. This event marked the end of the Dark Ages and signaled the birth of the first cosmic structures. Within about 150 million years after the Big Bang, structures such as early galaxies began to emerge, and this gradual process continued. By the time 1 billion years had passed, the Dark Ages had completely ended, and the universe began to resemble the vast, complex cosmos we observe today. Thus, the story of the universe's formation is one of constant evolution, of matter, light, and structure coming together across unimaginable timescales. From the formation of dark matter clumps to the birth of the first stars and galaxies, the universe's journey from an opaque, hot plasma to the diverse, transparent cosmos we observe today is a testament to the power of time, gravity, and the fundamental forces that shape the very fabric of reality. The universe, vast and full of mysteries, is still revealing its earliest moments to us, albeit in subtle glimpses. The oldest stars and galaxies we've observed thus far originate from just after the beginning of a pivotal process known as reionization. This process unfolded around 400 million years after the Big Bang, a transformative era in the history of the cosmos. Through the lens of the Hubble Space Telescope, astronomers have captured galaxies such as GN-Z11, which existed approximately 400 million years following the Big Bang. However, in 2021, the launch of the James Webb Space Telescope, JWST, brought a new era of cosmic discovery. With its superior power, JWST can detect galaxies that are 100 times fainter than those observed by Hubble. The telescope is expected to peer even further back in time, uncovering objects that may date as far as 180 million years after the Big Bang. This timeline potentially predates the formation of the first galaxies and might even reach back to the birth of the very first stars themselves. As astronomers continue to unlock the secrets of the universe's infancy, they focus on detecting a particularly faint form of radiation, the 21-centimeter spin line radiation. This form of radiation holds crucial information about the early universe, potentially more profound than the well-known cosmic microwave background radiation, which has already served as a key to understanding the universe's beginnings. While we have made substantial progress, the quest to precisely determine the timeline of the first stars, galaxies, black holes, and quasars continues. Equally challenging is pinpointing the exact start and conclusion of the reionization epoch. Each year brings new discoveries that further enrich our understanding. For instance, by 2019, scientists confirmed that galaxies such as GN-Z11 had existed roughly 380 to 400 million years after the Big Bang. This finding upended earlier assumptions, suggesting that gas clouds were condensing and forming stars far more rapidly than once believed. Additionally, the study of the Lyman alpha forest, an intricate pattern of light variations from distant objects, has helped researchers refine their estimates on when reionization began and ended. Yet, the mysteries of this period remain far from fully resolved. In the framework of the Big Bang model, the universe's structure evolved in stages. The first entities to emerge were the population 3 stars, massive primordial stars that contained only the lightest elements, hydrogen and helium. Alongside these early stars, tiny galaxies, dubbed dwarf galaxies, began to form. Perhaps the most captivating of these early structures were quasars, luminous active galaxies that housed supermassive black holes at their cores, surrounded by a swirling accretion disk of gas being drawn in at mind-boggling speeds. Before the formation of these early structures, the universe was mostly understood through a relatively simple theory: linear cosmological perturbation theory. This theory painted the universe as a largely uniform space, where the fluctuations were minute and changes occurred gradually. However, as the first stars and galaxies began to emerge, the complexity of the universe increased dramatically. Large clusters of particles began interacting in far more intricate ways, necessitating more advanced tools for study. Simulations involving billions of particles, known as n-body simulations, became essential for modeling the universe's evolution. The Bolloy cosmological simulation stands as one of the most sophisticated and accurate examples of these simulations, providing deep insights into cosmic phenomena. The population 3 stars weren't just the first to illuminate the universe. They also played a critical role in the creation of the heavier elements found in stars, planets, and ultimately life itself. These stars were born almost entirely from hydrogen and helium, with no heavier elements. Hence, they are termed non-metallic. The most massive among them had brief but intense lifespans, burning through their fuel in mere millions of years. Upon their death, they exploded as supernovae, scattering the heavier elements they had forged throughout the cosmos. These explosions marked the beginning of what is known as the Stelliferous Era, the period of ongoing star formation that would shape the future of the universe. Although no population 3 stars have been directly observed, their existence is inferred from sophisticated computer models designed to simulate their formation and evolution. Clues to their emergence also come from studying the cosmic microwave background radiation, the faint afterglow of the Big Bang. Data gathered by the Planck Space Telescope in 2016 suggested that the first stars began forming approximately 300 million years after the Big Bang, providing further evidence for the existence of these primordial giants. Quasars, some of the brightest and most energetic objects in the universe, also provide important clues about the universe's early days. The light emitted by quasars contains elements like carbon, magnesium, and oxygen, signaling that by the time quasars appeared, star formation had already been underway for some time. This includes several generations of population 3 stars whose explosive deaths produced these heavier elements. The powerful radiation from these early stars, dwarf galaxies, and quasars began to ionize the surrounding hydrogen gas, setting off a chain reaction that would eventually lead to the reionization of the universe. Reionization is the process by which the neutral hydrogen atoms that filled the early universe were split into their constituent protons and electrons, turning the gas into a plasma once again. This marked a significant turning point in cosmic history, as it reintroduced a state of ionized hydrogen that had not been seen since the era of recombination and decoupling, when the universe first cooled enough for atoms to form. Quasars are invaluable to our study of reionization, as their light reveals how hydrogen interacts with ultraviolet light. Neutral hydrogen absorbs ultraviolet light in distinct patterns, but once ionized, these absorption patterns vanish. By studying the light emitted from quasars, scientists can discern between ionized and neutral hydrogen, providing insights into the state of the universe during reionization. The study of ionized hydrogen also reveals the scattering of light through Thomson scattering, a process by which free electrons scatter light. However, by the time reionization began, the universe had expanded and matter had spread out significantly. As a result, the plasma of ionized hydrogen was much less dense, allowing light to pass through with fewer obstructions. The light from distant objects traveling across vast expanses of space was stretched out, its wavelength increased, leading to a phenomenon known as redshift. This stretching effect provides crucial information about the timing of reionization. Reionization likely started around 250 million years after the Big Bang, corresponding to a redshift of about 16. By 500 million years after the Big Bang, most of the universe had undergone reionization, reaching a redshift of 9 or 10. The final traces of neutral hydrogen were fully ionized by around 1 billion years after the Big Bang, corresponding to a redshift of 5 or 6. At this point, scientists stopped observing the distinct absorption patterns that had indicated the presence of neutral hydrogen. From that moment onward, the universe remained largely ionized, with only a few isolated pockets of neutral hydrogen remaining. These pockets are detectable in the light spectra we observe today as Lyman alpha forests, a unique feature that continues to aid astronomers in studying the universe's past. Despite our growing understanding of reionization's timing and progression, the specific causes behind it remain elusive. Reionization required a continuous source of energy greater than 13, 6 electron volts provided by ultraviolet light with wavelengths shorter than 91.2 nanometers. As such, the sources of this energy must have been incredibly powerful. The most likely candidates are the first stars, known as population 3 stars, along with dwarf galaxies and quasars. Current models suggest that population 3 stars played the most significant role in driving reionization, with smaller contributions from dwarf galaxies and quasars. By the time reionization occurred, the universe had undergone significant expansion. Matter had spread out and the density of hydrogen had decreased. The plasma, now much thinner, allowed light to travel more freely. As the process of reionization drew to a close, the universe became nearly transparent, with only a few regions of neutral hydrogen remaining. These regions continue to shape the light we observe today, offering a window into a past that remains as enigmatic as ever. In August of 2023, the James Webb Space Telescope unveiled a discovery that captivated the scientific community and ignited intense discussions across the globe. The telescope's remarkable ability to capture images of black holes and matter, dating back to the universe's earliest moments, brought an entirely new perspective to our understanding of cosmic evolution. What was once only theorized has now been observed with stunning clarity, deepening our understanding of the cosmos. At the heart of this discovery lies a fundamental principle. Matter, under the relentless pull of gravity, tends to clump together. Over immense periods, this process eventually leads to the formation of galaxies. However, the origins of these galaxies were not as straightforward as they might seem. During the universe's formative years, the stars that emerged were part of what scientists call population 2. These ancient stars formed in the very early universe, while the younger, more recent generation, known as population 1 stars, came into existence much later. Gravity's role in this cosmic drama extends beyond just the formation of stars. It plays a pivotal role in shaping the large-scale structure of the universe. As gravity pulls galaxies toward each other, they gradually form groups, clusters, and even vast superclusters. The Hubble Ultra-Deep Field observations, some of the most profound ever made, revealed smaller galaxies colliding and merging to form larger ones, about 800 million years after the Big Bang, or roughly 13 billion years ago. While this age estimate was initially considered accurate, newer evidence suggests it may have been a bit too high. Nonetheless, the patterns these discoveries reveal show that, for billions of years, the universe has followed a trajectory that mirrors its current state. And this trajectory is expected to persist for billions of years into the future. Among the many fascinating aspects of our cosmic history is the formation of the Milky Way's galactic disk, which is estimated to have begun around 8.8 billion years ago, though its exact age remains uncertain. The Sun, in comparison, has a well-established age, having formed about 4.6 billion years ago. These cosmic events unfolded roughly 9.8 billion years after the Big Bang, marking a significant turning point in the universe's evolution. It was during this period that the universe began to behave in a manner never observed before. In the earliest stages of its existence, the universe was dominated by radiation. Photons and neutrinos reigned supreme during the first 47,000 years. For the subsequent 370,000 years, matter began to take control, and gravity's influence gradually slowed down the expansion of space. However, something unprecedented happened around 9.8 billion years after the Big Bang. Instead of slowing down, the universe's expansion accelerated. The reason for this sudden and mysterious change remains one of the most profound, unsolved questions in modern physics. While the exact cause is still elusive, Most scientists believe that a mysterious force known as dark energy is responsible. The term dark in this context refers not to something we can see, but to something that we can only detect by its effects on the universe's gravitational dynamics. Current research suggests that dark energy comprises roughly 68.3% of the universe's total mass and energy, making it the dominant force in shaping the universe's evolution. Dark energy is thought to behave as a constant force throughout space, unlike gravity, which weakens with the expansion of the universe. As the universe stretches, the influence of gravity diminishes, but dark energy remains unchanged, continuing to push galaxies apart. Early in the universe's history, we saw distant objects moving apart as space itself expanded. As the universe continued to grow, the rate of separation between these objects slowed. Yet, over time, this slowing of separation became less and less noticeable. Eventually, the force of dark energy overwhelmed the pull of gravity, accelerating the universe's expansion rather than reversing it, as gravity might suggest. This shift marked a critical turning point in the cosmic story. The acceleration of expansion has only grown stronger over time, and it remains a defining feature of the universe's evolution today. As we look to the far future, different scenarios about the universe's ultimate fate have emerged, each depending on key factors such as the precise values of certain physical constants, the potential breakdown of protons, the building blocks of atoms, and the energy present in empty space. Beyond these known variables, there may exist deeper, as yet undiscovered laws of nature that could further shape the universe's destiny. If the universe continues its current path of accelerated expansion, it's possible that, in the distant future, the only galaxies observable to us will be those within our own local group, galaxies bound together by gravity. This process, occurring over vast spans of time, trillions of years from now, will mark the end of star formation. New stars will cease to form, and even the oldest stars will burn out and die. As this happens, the universe will grow colder, its energy dissipating as objects slowly cool and break apart. Over even longer periods, these remnants will decay into subatomic particles, eventually emitting faint energy in the form of low-energy photons. During this epoch, spanning across trillions of years, the universe will be a very different place, colder and quieter. However, within this incredibly distant future, the possibility exists for strange and rare events that could reshape reality in ways we cannot yet predict. Even the most stable phenomena, such as black holes, might vanish mysteriously. Quantum events, extremely rare occurrences that have no chance of happening within the lifetimes of humans or stars, might become more common in this far-flung era. These rare events, which might only occur once every trillion years, could become more frequent, altering the very fabric of space-time and the structure of the universe in ways that challenge our imagination. As we peer into the very origins of the universe, we step into the perplexing and often counterintuitive realm of quantum mechanics. This is a domain where the very notion of nothingness is radically transformed. What we once understood as empty space, devoid of matter or energy, is in fact a bustling, dynamic realm filled with invisible, ceaseless activity. At the heart of this revelation lies a concept that has revolutionized our understanding of reality: quantum fluctuations. Quantum fluctuations are tiny, unpredictable bursts of energy that occur in the vacuum of space. For centuries, empty space was assumed to be just that, truly empty. Yet modern physics has shown that this is far from the case. In fact, the vacuum of space is teeming with fleeting bursts of energy, with particles flickering in and out of existence. These fluctuations arise from the uncertainty principle, a cornerstone of quantum mechanics, proposed by the physicist Werner Heisenberg. According to the uncertainty principle, it is impossible to know both the exact position and momentum of a particle simultaneously. This inherent uncertainty gives rise to fluctuations even in the vacuum of space, where we once expected stillness. These fluctuations form the basis of what we now call quantum foam, an invisible, chaotic churn of energy at the smallest scales of reality. The idea that empty space could be so alive with energy gained experimental validation in 1947 through the pioneering work of Dutch physicists Hendrik Casimir and Dirk Polder. Their experiment, which involved placing two uncharged metal plates very close together in a vacuum, provided the first solid evidence of what would become known as the Casimir effect. According to classical physics, nothing should happen in this scenario, but their findings demonstrated that even in a vacuum, strange and unexpected forces could arise. This discovery marked the beginning of a profound shift in our understanding of the universe, revealing that even the most empty regions of space are, in reality, far from empty. Instead, they are filled with the potential for infinite fluctuations, shaping the very fabric of the cosmos in ways that are only just beginning to be understood. And as we delve deeper into this strange quantum realm, we uncover the mysteries that govern the universe, knowing that many more await discovery. The journey of the universe's creation is one that defies conventional understanding, unfolding in a way so unexpected that it challenges everything we think we know about the origins of existence. Imagine standing on the edge of reality, witnessing something extraordinary that turns the conventional order upside down. This was the reaction when scientists first observed an anomaly, a strange, invisible force seemingly pulling two plates toward each other. What made this so baffling was the fact that the plates weren't touching, yet they were drawn closer, as if some unseen power was at work. The answer to this phenomenon lay deep within the realm of quantum mechanics, in the subtle, often overlooked fluctuations of the quantum field. This force, known as the Casimir effect, became a startling revelation. It proved that even in the emptiness of a vacuum, there was something invisible, yet undeniably real. The space between the plates was so minuscule that it suppressed certain quantum fluctuations, creating an imbalance of pressure. This imbalance, in turn, gave rise to an attractive force that pulled the plates together. For the first time, the concept of empty space was called into question. If even a vacuum is teeming with energy, what else might lie hidden within it? The discovery of the Casimir effect was nothing short of groundbreaking. It confirmed that the vacuum, often regarded as a void, is not empty at all. Instead, it is a space filled with potential energy, an invisible sea of quantum fluctuations. This subtle energy, in turn, reshapes our understanding of physics, suggesting that even the most barren stretches of space contain a level of activity that remains unseen but profoundly impactful. With this new insight, scientists began to entertain the possibility that these fluctuations, these fleeting, almost imperceptible shifts in energy, could have played a role in the birth of the universe itself. In fact, many of the leading theories in cosmology suggest just that. Some propose that the very fabric of the universe might have emerged from these quantum fluctuations in a primordial vacuum. A state we often call nothing might have, in reality, been brimming with these tiny bursts of energy. Under the right conditions, one of these fluctuations could have expanded exponentially, sparking the event we know as the Big Bang. The universe, it seems, could have erupted not from absolute nothingness, but from a state where energy already existed, waiting for the right moment to burst forth. This idea aligns with key principles in modern physics, such as quantum field theory and cosmic inflation. Both concepts propose that the universe didn't simply come into being from a singular event out of nowhere. Rather, it emerged from a quantum fluctuation, an event driven not by an external creator, but by the inherent potential of the quantum vacuum itself. These quantum fluctuations, though often regarded as insignificant, possess the power to shape the cosmos in profound ways. They challenge our assumptions about reality, urging us to rethink the very nature of space, energy, and existence. Quantum mechanics, with its strange and counterintuitive principles, now presents a compelling case for how the universe may have evolved from what appeared to be an empty void. In this new paradigm, even the most seemingly insignificant fluctuations can have monumental consequences. It turns out that the universe, in all its vastness, might have emerged from these infinitesimal disturbances in the quantum field. These fluctuations, which seem random and inconsequential at first, can have a ripple effect across time, setting the stage for the formation of the cosmos as we know it. The implications of this discovery are staggering. For instance, after the Big Bang, the universe was in an extreme state of heat and energy. At that time, quantum fluctuations may have acted as the seeds for the vast, complex structure of the universe we observe today. These fluctuations, while too small to be detected initially, would have left subtle imprints on the density of space itself. Gravity, in turn, began to pull on these irregularities, shaping them over time into the galaxies, stars, and other cosmic structures that we now see scattered across the universe. This theory of cosmic inflation offers further insight into the rapid expansion of the universe just after the Big Bang. According to this idea, the universe expanded faster than the speed of light in the moments following its inception, and quantum fluctuations were stretched across vast regions of space during this brief yet intense period. These fluctuations left behind tiny variations in density, which, over billions of years, would give rise to the formation of stars, galaxies, and clusters of matter. Essentially, the universe's grand structure is the result of these early fluctuations magnified by gravity and time. However, this only scratches the surface of what quantum fluctuations may reveal about the cosmos. Some scientists propose a more radical idea. What if the entire universe itself emerged from a single quantum fluctuation? This theory suggests that the universe didn't require a pre-existing cause or an external creator to come into being. Instead, it could have simply popped into existence from the quantum vacuum, a space that, contrary to our expectations, is filled with untapped energy. In this view, the creation of the universe would have occurred spontaneously, driven by the fundamental forces within the quantum field, without a traditional cause and effect relationship. This challenges the conventional wisdom we hold about cause and effect. In the quantum world, the vacuum itself is not empty, but full of potential. From this perspective, creation doesn't need a prior cause, but can emerge out of the quantum field itself. Under the right conditions, particles can materialize and vanish in an instant. So too could entire universes. This radical rethinking of how the universe came into being challenges everything we thought we knew about reality, offering a view of creation that is as unpredictable as it is awe-inspiring. While this theory is still in its early stages, it presents a fascinating possibility for how the universe might have originated. It paints a picture of creation that doesn't adhere to traditional notions of cause and effect, suggesting that the line between nothingness and somethingness is not as clear as it seems. In this quantum world, what appears to be empty space could be a fertile ground for the seeds of all possibilities. Seeds that, when the moment is right, can sprout into galaxies, stars, and life itself. The idea that the universe could have come from nothing might seem incomprehensible, but quantum mechanics provides us with a plausible framework to understand this. It offers us a view of the universe where creation is not a singular event but an ongoing, dynamic process. In the quantum field, every moment holds the potential for something new to emerge. The very nature of existence itself might not be a static, unchanging state, but a continuous cycle of creation, destruction, and rebirth, a dance of energy that never ceases. If we extend this thinking further, we begin to understand that the universe is not simply a product of some ancient, one-time event. Instead, it is a constantly evolving system, where energy fluctuations ripple through the quantum vacuum, giving birth to new structures, new realities, and potentially even new universes. This view of the universe as a living, ever-changing entity opens up a new realm of exploration, where science, philosophy, and metaphysics converge to answer some of the deepest questions about existence. From this perspective, the creation of our solar system, Earth, and life itself is not a random accident, but a story that began billions of years ago with the chaotic remains of dead stars. Our solar system, like the universe, was born out of violence, energy, and cosmic evolution. Over 4.6 billion years ago, the remnants of a supernova, a massive stellar explosion, sent shockwaves through a cloud of gas and dust, triggering the formation of our solar system. This once unremarkable cloud collapsed under the force of gravity, spinning faster and faster, eventually flattening into a disk. As the material in this disk clumped together, it gave birth to the planets, moons, and the sun itself. The sun's birth ignited the entire process, drawing in more material and forming planetesimals, small, rocky bodies that would eventually coalesce into planets. Earth, one of these planets, became the cradle of life, shaped by the very forces that shaped the cosmos. The story of our solar system's formation is just one chapter in the grand narrative of the universe's evolution. It's a story filled with chaos, violence, and incredible transformation. And as we continue to explore the mysteries of quantum fluctuations, the birth of stars, and the formation of planets, we begin to realize that the universe is far more dynamic and interconnected than we ever imagined. It is a universe driven by unseen forces, where the boundary between nothing and everything is not as distinct as we once thought. And perhaps, just perhaps, it is a universe that is still in the process of unfolding. The early solar system, contrary to the peaceful, serene image we might have today, was a wildly chaotic, violent place. It was a time of fierce collisions, a battleground where planetesimals, small rocky or icy objects, constantly slammed into each other, merging, smashing apart, or sometimes joining forces to create larger, more formidable bodies. This continuous cosmic destruction and rebirth eventually gave rise to the four inner rocky planets: Mercury, Venus, Earth, and Mars, all of which formed in close proximity to the Sun. Meanwhile, farther from the Sun, in the colder reaches of the solar system, the gas giants, Jupiter and Saturn, and the icy giants, Uranus and Neptune, began to take shape. The process of forming these planetary bodies was anything but a smooth or orderly one. It was messy, unpredictable, and at times violently chaotic, with bodies repeatedly colliding and interacting in ways that shaped the future of the solar system. Over millions of years, the intense collisions between small planetesimals contributed to the gradual accretion of mass, with each crash adding a little more material and slowly building up the planets bit by bit. As time passed, the inner planets developed solid surfaces and atmospheres, but each followed a different path. Venus and Mars, for example, became worlds entirely different from Earth. Earth, however, took a unique trajectory, one that would lead it to become the only known planet capable of supporting life. Now, looking beyond the region known as the frost line, the boundary in the solar system where temperatures dropped low enough for gases such as water, methane, and ammonia to freeze into ice, the formation of the gas giants began. These colossal planets, Jupiter, Saturn, Uranus, and Neptune, began as rocky cores, but their immense size allowed them to capture large amounts of gas from the surrounding solar nebula, the cloud of gas and dust left behind after the sun was born. This ability to accumulate vast quantities of gas enabled them to grow into the massive, swirling gas giants we see today. Among these gas giants, Jupiter stood out. Its sheer size allowed it to have a profound influence on the solar system's structure. Its immense gravity may have even prevented the formation of other planets further out in the system. It altered the orbits of objects nearby, molding the architecture of the entire solar system. But while the formation of these massive gas giants was awe-inspiring, the true marvel lay closer to the Sun, where Earth, in the midst of all this chaos, was slowly becoming a planet unlike any other. Earth is, without a doubt, the most unique planet in our solar system. It is the only one known to harbor life, and it has been our home for billions of years. What makes Earth so special? Why is it the only planet, as far as we know, capable of sustaining life? The answer lies in an intricate and harmonious combination of factors that came together in just the right way. Earth's position relative to the Sun, its atmosphere, magnetic field, and the presence of water all played vital roles in making Earth the ideal environment for life to flourish. One of the most crucial elements of Earth's ability to support life is its location in the habitable zone, the region around a star where temperatures are just right to allow liquid water to exist. This Goldilocks zone, where the conditions are neither too hot nor too cold, is what makes Earth the perfect place for life as we know it. Earth's average distance from the Sun is about 93 million miles, which means it is just the right distance to allow water to remain in liquid form on its surface. Without this perfect positioning, life as we understand it could not have evolved. Liquid water is essential for life. On planets like Venus, which are too close to the Sun, intense heat causes water to evaporate, leaving the planet dry and inhospitable. On the other hand, Mars, being farther from the Sun, is too cold for liquid water to remain on its surface. Any water there would freeze, creating an environment hostile to life. But on Earth, water exists in all three forms: liquid, solid, and gas. This remarkable ability allows Earth to create an environment where life can thrive in a variety of ways, from the tiniest microorganisms to the largest animals. Another critical factor in Earth's habitability is its atmosphere. Earth's atmosphere acts like a protective blanket, wrapping the planet in layers of gases that perform two essential functions: protecting the surface from harmful radiation and helping to regulate the planet's temperature. Without this shield, Earth would be exposed to the harsh conditions of space, and life could not survive. In addition to the atmosphere, Earth's magnetic field plays a key role in protecting the planet from solar radiation. Generated by the movement of molten iron in Earth's core, the magnetic field acts as a deflector, pushing harmful solar winds away from the planet. Without this magnetic shield, Earth's atmosphere would be slowly stripped away, and life would face the same fate as it did on Mars: impossible. Earth's most defining feature, however, is its abundance of water. Often referred to as the blue planet because more than 70% of its surface is covered by oceans, Earth is the only planet in our solar system where liquid water exists in such abundance. Water is vital for all known forms of life, sustaining life, providing nutrients, and regulating Earth's temperature. The sheer amount of water on Earth is one of the primary reasons life is able to thrive here, from microscopic life forms to complex organisms. Earth's geological activity also plays a significant role in its habitability. The movement of tectonic plates, the large segments of Earth's crust that are constantly shifting, helps maintain the planet's long-term stability. The process of plate tectonics is crucial for recycling nutrients and regulating Earth's temperature. It is also responsible for creating mountains, earthquakes, and volcanic activity, which all contribute to Earth's dynamic and ever-changing nature. This geological activity helps to stabilize the planet's climate, providing a stable environment that has allowed life to evolve and thrive for billions of years. So, how did Earth and the other planets form in the first place? What processes led to their creation, and why did Earth end up in such a perfect position for life? To understand this, we must delve into the theories of planetary formation, explanations of how planets emerged from the dust and gas of the early solar system. The formation of planets is a fascinating process that has intrigued scientists for centuries. With advancements in technology such as powerful telescopes and sophisticated computer simulations, we've gained a deeper understanding of how planets form, but many questions remain. The most widely accepted theory explaining planetary formation is the nebular hypothesis. According to this theory, when a star is born, it is surrounded by a cloud of gas and dust known as a nebula. This nebula is composed of leftover materials from the formation of the star itself. Planets begin to form from this material as it condenses and clumps together under the influence of gravity. The process begins with the formation of a rotating disk of gas and dust around the young star. As this material orbits the star, small particles of dust and ice collide and stick together, forming larger objects called planetesimals. These planetesimals are the building blocks of planets. Over millions of years, these planetesimals continued to collide and merge, gradually growing into larger bodies called protoplanets. These early versions of planets eventually grew large enough to become full-fledged planets. This process, known as accretion, explains how rocky planets like Earth and Mars formed close to the Sun, while gas giants like Jupiter and Saturn formed farther out, where more gas was available. The formation of gas giants like Jupiter and Saturn followed a slightly different path. These planets began with the formation of solid cores made of rock and ice. Once these cores grew large enough, they could attract huge amounts of gas from the surrounding nebula, allowing them to become massive planets with thick atmospheres. The key factor in the formation of gas giants is that they formed far from the Sun, where there was more gas available for them to gather. Over billions of years, the process of accretion continued, shaping the planets and their moons. The leftover gas and dust did not simply form planets, but also created comets, asteroids, and other small objects that we continue to encounter in the solar system today. The theory of core accretion provides a compelling explanation for the formation of gas giants. According to this theory, these massive planets started as rocky cores, and over time their gravity allowed them to pull in vast amounts of gas, forming thick, dense atmospheres. This process worked best for planets that formed farther from their star, where there was more gas to collect, allowing these planets to grow into the gas giants we see today. The remarkable differences between the planets. whether rocky or gas giants, are a direct result of where they formed in the solar system and how they interacted with the gas and dust that once filled the young solar system. Another theory, known as disinstability, presents a radically different approach to our understanding of how gas giants might form. Unlike the widely accepted core accretion model, which suggests that gas giants form slowly by gathering gas over time, this theory proposes that gas giants could form much more rapidly. It suggests that these massive planets arise from the sudden collapse of gas in dense regions of a gas disk surrounding a young star. This collapse happens much faster than the gradual accumulation of gas, allowing gas giants like Jupiter to take shape in mere millions of years. Such a rapid formation could help explain how gas giants formed early enough in the history of the solar system to prevent the intense solar wind from blowing away the gas that enveloped the young solar system. Without this early formation, much of the potential for planet growth would have been lost. Today, scientists have access to incredibly advanced telescopes that allow them to observe the birth of planets in distant star systems. Instruments such as the Atacama Large Millimeter Submillimeter Array, ALMA, and the James Webb Space Telescope have revolutionized our understanding by giving us a clearer view of how planets are forming in other parts of the universe. These powerful telescopes have captured detailed images of protoplanetary disks, vast clouds of gas and dust swirling around young stars. These swirling clouds serve as the raw material from which planets are born. As the dust and gas in these disks rotate and interact, small building blocks known as planetesimals collide and merge. Over time, these collisions lead to the creation of full-fledged planets, just as they did in our own solar system. What this means is that the formation of our solar system was not as unique as we once believed. It is part of a much larger, more universal process happening throughout the cosmos. The birth of our solar system, long shrouded in mystery, began with a chaotic and violent stage. A massive cloud of gas and dust, a remnant of older stars, collapsed under its own gravity. As it did, the energy released ignited the formation of the sun, while violent collisions among the particles of dust and gas contributed to the creation of the planets. This process, though incredibly slow, spanned billions of years, eventually leading to the stable orbits that the planets now follow. Each planet has its own unique characteristics, shaped by the forces of gravity, gas, and time. Earth, in particular, is a planet that emerged under very special conditions that allowed life to take root and thrive. Living on Earth, we are part of an extraordinary cosmic journey. The same forces that shape the planets in our solar system continue to shape planets in other star systems across the vast reaches of space. For millennia, humans have gazed up at the night sky, pondering an age-old question. Are we alone? Is Earth the only place in the expanse of the universe where life can thrive? Or might there be other planets distant from our own where life exists or has already taken root? This question has captivated the imaginations of philosophers, scientists, and dreamers alike. It challenges everything we know about the universe, pushing the boundaries of science and imagination. Thanks to technological advancements in telescopes and space exploration, we are now closer than ever to answering this profound question. The search for extraterrestrial life, life that exists beyond our Earth, is one of the most exciting and profound pursuits in modern science. It takes us on an incredible journey, not only to exoplanets orbiting distant stars, but also to the farthest reaches of our own solar system. As we venture deeper into the unknown, scientists are compelled to reconsider what it means to be alive and what conditions are necessary for life to emerge. They study the unique properties that make Earth habitable, and using advanced tools, they explore the possibility of life elsewhere. This includes the search for extraterrestrial intelligence, hoping to discover signals from civilizations far out in space, or perhaps even find proof that we are not the only ones in the universe. Here on Earth, life flourishes in a dazzling array of forms, from the tiniest single-celled bacteria to the largest and most complex mammals. But what makes Earth so uniquely capable of sustaining life? What are the specific conditions that make our planet so special? Scientists believe that by understanding these conditions, we may one day be able to identify other planets that share similar features, planets where life could exist. One of the most fundamental ingredients for life, as we know it, is liquid water. Water is absolutely essential for life on Earth. It serves as a solvent, dissolving substances, and enabling the chemical reactions necessary for biological processes. It also plays a critical role in transporting nutrients, regulating temperature, and maintaining the structural integrity of cells. Without water, life would not be possible. So why is Earth fortunate enough to have liquid water? The answer lies in its position within a very specific region around the Sun, the habitable zone. The habitable zone is the region around a star where the conditions are just right for water to remain in liquid form, not too hot and not too cold. Planets that are too close to their star, like Venus, are too hot, causing any surface water to evaporate. On the other hand, planets that are too far away, like Mars, are too cold, causing water to freeze. Earth occupies a sweet spot where the temperature is just right for liquid water to exist, making it the perfect environment for life to flourish. In addition to liquid water, life on Earth also requires a steady source of energy. On our planet, the primary energy source comes from the sun. Through the process of photosynthesis, plants capture this solar energy and convert it into a form that other organisms, such as animals, can use by eating plants or other animals. The energy from the sun drives everything from the smallest plant to the largest predator, fueling the cycles that sustain life on Earth. As scientists continue to explore other worlds, their search for signs of life extends beyond just water and energy. They seek planets with the right atmospheric conditions, the right mix of chemicals, and the right distance from their parent star to allow life to take root. As we look further into the cosmos, we may be on the brink of discovering that life, in some form, exists elsewhere, waiting to be found. The journey to answer this question is far from over, and with every new discovery, we come closer to understanding our place in the vast, mysterious universe. Deep beneath the surface of Earth's vast oceans, in the shadowy depths far removed from the warm embrace of sunlight, an extraordinary form of life thrives. Around hydrothermal vents, cracks in the Earth's seafloor that spew heat and chemicals from the planet's very core, an entirely different ecosystem flourishes, one that does not depend on the sun's energy to survive. Instead, life here relies on the heat and minerals pouring from these underwater fissures, harnessing the energy from the planet's internal processes rather than from the external warmth of the sun. These organisms, often strange and otherworldly in appearance, reveal that life is far more adaptable and resilient than we once thought. These creatures demonstrate that life can exist in conditions that would be inhospitable to most known species, where temperatures soar, pressure is crushing, and no sunlight ever penetrates. This discovery, hidden beneath the ocean's surface, has forced scientists to rethink what it takes for life to survive. It challenges our long-held assumption that life must be sustained by sunlight and oxygen, introducing a whole new world of possibilities for where life could exist elsewhere in the universe. If life can endure in these extreme deep-sea environments on Earth, then the chances of life surviving in similarly harsh conditions on other planets or moons becomes far more plausible. Could there be other places far from the sun's rays where life may take root? Perhaps moons like Europa, which orbits Jupiter, or Enceladus, a moon of Saturn, might harbor the right conditions for life, beneath their icy exteriors, in oceans kept warm by their planet's gravitational pull. Life on Earth is undoubtedly dependent on many factors, but perhaps the most critical of these is the stability of its environment. Without stable conditions, life as we know it simply cannot develop or thrive. Picture a tree struggling to grow in soil that lacks nutrients, in a place where sunlight is scarce and water is unpredictable. The tree won't survive, let alone flourish. Earth's stability is key to its ability to sustain life. The planet's climate, its rotation, its distance from the sun, these all combine to create an environment where life can evolve and endure over millions, even billions of years. But the bigger question remains, can other planets in our galaxy offer these same conditions? Do they have the right ingredients for life to grow and evolve, just like Earth does? A planet capable of supporting life needs more than just the basics: water, a stable climate, and a food supply. Perhaps the most vital requirement is an atmosphere, a protective blanket that shields life from the harsh conditions of space. Earth's atmosphere plays several crucial roles. It protects us from harmful cosmic radiation, regulates temperatures to keep them within a livable range, and safeguards us from the destructive force of solar winds. Without this atmosphere, Earth would be nothing more than a barren frozen rock, bombarded by radiation. Life would struggle to survive, if not entirely perish. So, when we think about whether other planets can support life, the question we must ask is, do they have the same atmospheric protections that Earth does? For a planet to have a chance at harboring life, it needs an atmosphere capable of blocking harmful radiation, regulating temperatures, and protecting it from solar winds. And it doesn't stop there. A planet needs a magnetic field to help shield it from cosmic rays, something that Earth benefits from due to its iron-rich core and molten outer layers. Without these protective features, any planet in the vastness of space would be exposed to lethal levels of radiation, making it incredibly difficult, if not impossible, for life to thrive. As the search for life beyond Earth continues, scientists are drawn to a mathematical framework designed to tackle this very question. Enter the Drake equation, a tool developed in 1961 by astronomer Frank Drake to estimate the number of technologically advanced civilizations that might exist in our galaxy. While the equation was originally intended to calculate the likelihood of civilizations capable of communicating with us, it has become a fundamental way of thinking about the search for extraterrestrial life. The equation breaks down the search into manageable parts, asking critical questions at each step. For example, how many stars in our galaxy have planets? Of those planets, how many could have the right conditions to support life? Out of these, how many might go on to develop intelligent life? And of those civilizations that develop intelligence, how many will be able to communicate across the vast distances of space? Despite its simplicity, the Drake equation is a powerful tool. It's not meant to provide a definitive answer, but rather to guide us in understanding the complex variables that influence the potential for intelligent life elsewhere in the universe. It encourages us to consider not only the physical characteristics of planets, but also the numerous factors, some still unknown, that contribute to the emergence of life. Yet, as we continue to search the cosmos, one question looms large. If intelligent life is as common as we suspect, why haven't we heard from anyone yet? This conundrum, known as the Fermi paradox, remains one of the most perplexing mysteries of modern science. In 1950, the renowned physicist Enrico Fermi posed a simple but profound question. Where is everybody? With so many stars in the universe, and with the likelihood of many planets hosting intelligent life, why haven't we detected any signals or signs of these civilizations? The paradox highlights the contradiction between the seemingly high probability of life elsewhere and the complete lack of evidence for it. The sheer scale of the universe, coupled with the increasing number of potentially habitable planets discovered by astronomers, makes it seem almost inevitable that intelligent life should exist somewhere. And yet, despite decades of searching, we have found no clear evidence of extraterrestrial civilizations. Many theories attempt to explain the Fermi paradox, but none are conclusively proven. One possibility is that intelligent civilizations are exceptionally rare, so rare, in fact, that they are difficult to detect. Perhaps life exists in the universe, but it hasn't yet evolved to the point of developing the advanced technologies necessary for long-distance communication or space travel. Another theory suggests that intelligent civilizations may simply not last long enough to develop such technologies. They might self-destruct through war, environmental collapse, or some other catastrophic event before they can signals or venture out into space. Yet another idea proposes that the civilizations we are looking for might be so distant, or their signals so faint, that we simply haven't detected them. Moons in our own solar system, like Europa and Enceladus, hold tantalizing possibilities. Beneath their thick icy shells lie vast oceans warmed by the gravitational forces of their parent planets. Could life be hiding beneath these frozen crusts? Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, may seem like barren, frozen worlds at first glance, but the evidence suggests that beneath their icy surfaces, the necessary ingredients for life could very well be present. The search for life beyond Earth continues, driven by the possibility that we may one day discover something truly extraordinary. Whether it's a signal from an intelligent civilization, the discovery of a new exoplanet, or the unveiling of hidden life in the icy depths of our own solar system, each new finding brings us one step closer to answering the ultimate question: are we alone in the universe? However, scientists believe that beneath the frozen exterior of certain moons in our solar system lies a world of extraordinary potential. These moons, with their thick, icy shells, conceal vast, hidden oceans of liquid water, oceans that might harbor the perfect conditions for life to take hold. Water, as we know, is a fundamental building block for life, and these concealed seas could provide an environment that supports living organisms, even in the harshest, most extreme conditions. Europa, one of Jupiter's moons, has long been the subject of intense scientific curiosity. NASA's upcoming Europa Clipper mission is poised to launch soon, with the goal of closely examining this intriguing moon, investigating its ocean, ice, and surface features in search of signs of life. The mission's scientists are especially eager to determine if Europa's environment could mirror the conditions found here on Earth, particularly in the depths of our oceans, where life thrives around deep-sea vents far removed from sunlight. In a similar vein, Enceladus, another moon, this one orbiting Saturn, has captivated researchers ever since 2005. That year, NASA's Cassini spacecraft made a remarkable discovery. Enceladus emits plumes of water vapor from cracks in its icy shell. These plumes, scientists believe, are the telltale signs of a liquid ocean lurking beneath the ice, and they may contain the chemical ingredients necessary for life. If microbes exist within this hidden ocean, it could be a monumental step toward proving that life can exist beyond the boundaries of Earth. What makes these moons so compelling is that they offer a glimpse into how life could persist in places far removed from our sun. If life can survive in the subsurface oceans of Europa or Enceladus, it could change our perspective on the possibilities for life in the cosmos. Perhaps in the future we will discover other icy moons or planets currently unknown that could harbor life in ways we've never imagined. The search for extraterrestrial life is one of the most profound and exciting quests humanity has ever embarked upon. It challenges us to reconsider everything we know about life, the universe, and our role within it. Are we truly the only intelligent beings in the vast reaches of the cosmos? Or are there others out there, waiting to be discovered, hidden just beyond our grasp? Each new finding, whether it's the detection of a distant exoplanet, an anomalous signal from the farthest reaches of space, or the discovery of hidden water beneath a thick crust of ice, brings us a little closer to answering that age-old question. For nearly 14 billion years, the universe has been expanding, evolving, and changing in ways that we are only beginning to understand. Stars have been born, galaxies have collided, and planets like Earth have formed, providing the conditions for life to emerge. Yet, as we peer deeper into the cosmos, we are confronted with a sobering realization: nothing lasts forever, not even the universe itself. This vast, ever-expanding universe, which has given rise to all that we know, is slowly and inexorably journeying toward its end. As scientists continue their observations, one question reverberates through their minds: how will the universe meet its ultimate fate? The answer to this question is entwined with the cosmic forces that shape the very fabric of the universe: gravity, dark matter, and the mysterious force known as dark energy. These forces interact in complex ways, playing pivotal roles in determining the universe's fate. Over the course of this exploration, we will examine the most compelling theories regarding how the universe might come to its end, from a slow, cold death in a scenario known as the Big Freeze, to a violent, catastrophic disintegration in a theory called the Big Rip, and even a potential rebirth through a cosmic collapse known as the Big Crunch. Each of these possibilities offers a haunting glimpse into the far future of the universe, raising profound questions about the stars, galaxies, and black holes that light up the night sky today. Will these celestial bodies survive as time marches on, or will they too meet their cosmic end? The universe has been expanding ever since the Big Bang, and this expansion continues to this day. However, how this expansion will ultimately end hinges on the delicate balance between two opposing forces: gravity and dark energy. Gravity, the force that pulls objects together, and dark energy, the enigmatic force that pushes the universe apart, are locked in an ongoing struggle for dominance. Dark energy is particularly mysterious. It is the force responsible for the accelerated expansion of the universe. But scientists remain largely uncertain about its true nature and how it functions. Despite these mysteries, dark energy plays a crucial role in determining the fate of the cosmos. It holds the key to understanding whether the universe will expand forever or eventually reach a dramatic end. Over time, scientists have developed several theories about how the universe might meet its end, each shaped by the interactions between gravity, dark energy, and the fundamental laws of physics. One of the most widely accepted theories is known as the Big Freeze, or the heat death of the universe. In this scenario, dark energy continues to drive the universe's expansion, causing it to grow at an ever-accelerating rate. As galaxies drift farther and farther apart, the universe grows colder, emptier, and more isolated. Over billions of years, stars will burn through their fuel one by one and eventually die. Some will leave behind remnants such as white dwarfs, neutron stars, and black holes, but with no new stars being born, galaxies will gradually fade. Eventually, the universe will become a cold, dark, and empty void. The last remaining stars may burn for trillions of years, but eventually, even they will run out of fuel, and the universe will be left in a state of eternal frozen stillness. This slow, quiet end is a cosmic big freeze, where entropy, the measure of disorder, will reach its peak, and all energy will be evenly spread across the universe, leaving no energy available to fuel life or any processes. However, there are other, more dramatic possibilities for the universe's end, particularly if dark energy behaves in ways that we cannot yet fully predict. One such theory is the Big Rip. In this scenario, dark energy doesn't merely cause the universe to expand. It accelerates this expansion at an ever-increasing rate. Over time, the force of dark energy becomes so powerful that it begins to tear apart not only galaxies, but also stars, planets, and even atoms. At first, the effects of the Big Rip would be subtle. Galaxies would drift farther apart, just as they do in the Big Freeze. But eventually, the expansion would accelerate so rapidly that the very fabric of space and time would begin to unravel. First, galaxies would break apart, followed by the disintegration of stars, the tearing of planets from their stars, and finally the complete dissolution of atoms and subatomic particles. The universe would end in a violent, catastrophic event, with space itself collapsing into nothingness. If dark energy continues to grow stronger over time, this theory could indeed come to pass, resulting in the disintegration of everything we know. But what if, in the distant future, gravity wins? Could it reverse the expansion of the universe, pulling everything back together? In this case, the Big Crunch scenario takes center stage. Gravity begins to overpower dark energy, slowing the expansion and eventually reversing it. Over billions of years, galaxies, stars, and planets once drifting apart would start to converge. As this process continues, galaxies would collide, stars would merge, and the universe would shrink. This collapse would lead to an increasingly dense and hot universe, continuing until everything, galaxies, stars, planets, was crushed into a singular point, similar to the singularity from which the Big Bang originated. This singularity would represent a moment of infinite density and heat, possibly leading to the birth of a new universe. In this view, the universe would not end in a final death, but instead undergo an eternal cycle of creation, collapse, and rebirth. These theories, Big Freeze, Big Rip, and Big Crunch, offer us distinct visions of the universe's future, but all hinge on the behavior of dark energy. The ultimate fate of the universe depends on this mysterious force. Will it continue to make the universe expand faster? Will it grow stronger over time, leading to the violent dissolution of everything in the Big Rip? Or will gravity eventually dominate, reversing the expansion and bringing about the Big Crunch? At present, we don't know for sure. The future of the universe remains uncertain, but we do know that dark energy will play a crucial role in shaping its eventual end. In the year 1998, a groundbreaking discovery shifted our understanding of the universe. Astronomers had long believed that the universe's expansion would gradually slow down due to gravity, but instead, they found that the expansion was speeding up. This unexpected revelation led to the concept of dark energy, a mysterious force responsible for this accelerated expansion. Dark energy is now believed to make up about 68% of the universe, yet its exact nature remains elusive. Some scientists speculate that dark energy could be a constant force known as the cosmological constant, existing uniformly across empty space. Others believe dark energy could be more dynamic, fluctuating in strength over time. If dark energy is a constant, the universe will keep expanding forever, but it will gradually slow down, leading to the cold, lifeless death known as the Big Freeze. Alternatively, if dark energy becomes stronger over time, the universe could end in the catastrophic Big Rip. Understanding the true nature of dark energy is one of the greatest challenges in modern science, and solving this mystery could unlock the secrets of the universe's ultimate fate. While these speculations focus on the far future, it's also worth considering the fate of individual stars, galaxies, and black holes, which will all meet their own ends long before the universe itself concludes its journey. Over the coming trillions of years, the fate of these celestial objects will unfold, offering valuable insights into the universe's overall future. Stars, those brilliant beacons in the vastness of space, are born, evolve, and eventually die. Just as all living things have a finite lifespan, stars too will eventually run out of fuel. Our own sun, for instance, is about 4.6 billion years old and has approximately 5 billion years left before it exhausts its nuclear fuel. As stars approach the end of their lives, their transformations are nothing short of spectacular. Smaller stars like red dwarfs burn their fuel slowly and can live for trillions of years, outlasting even our sun. These stars will be the last to fade into the darkness, hanging on longer than anything else in the universe. Larger stars, however, go out with a bang. As they run out of fuel, they expand into massive red giants, many times larger than their original size. In this phase, they shed their outer layers, creating a stunning nebula. What remains is a white dwarf, a dense remnant of the star that will gradually cool over billions of years. For the most massive stars, their deaths are even more dramatic. They end in a powerful explosion known as a supernova, a burst of energy so intense that it can briefly outshine entire galaxies. What's left behind could either be a neutron star or a black hole, both of which are remnants of incredible density. Black holes, with their unfathomable gravity, are some of the universe's most mysterious objects. Nothing, not even light, can escape their grasp. Yet, even these seemingly invincible remnants are not immune to the passage of time. Over unimaginable stretches of time, even black holes will slowly lose mass due to a process known as Hawking radiation. Though this process is incredibly slow, it will eventually cause black holes to evaporate, leaving behind a universe devoid of matter, empty and dark. Meanwhile, galaxies like our Milky Way, currently in a slow dance with its closest neighbor, the Andromeda Galaxy, will eventually collide and merge into larger, more massive galaxies. These cosmic mergers will reshape the universe in ways we are only beginning to understand. But ultimately, everything, galaxies, stars, and black holes, will fade, and the universe will continue its journey toward its final, unknowable end. However, this expansion, fueled by the mysterious force of dark energy, will not last forever. Dark energy is the enigma that drives the ever-accelerating expansion of the universe, pushing galaxies farther apart with each passing moment. As time stretches forward, these vast galaxies will become increasingly isolated, pulled away from one another until they drift alone in the cosmic void. The gas necessary for star formation will gradually be depleted, and without the birth of new stars, the old ones will eventually burn out. Without fresh light to replace the dying stars, the galaxies themselves will begin to fade, their once vibrant lights dimming into the blackness of space. As stars exhaust their fuel and no new ones are born, the universe will slowly succumb to an everlasting twilight. It will become a place of chilling emptiness, where the remnants of stars that once lit up the night are all that remain. These remnants, cold and inert, will drift through space, leaving behind a universe devoid of energy, motion, and life. The galaxies, now dark and desolate, will wander aimlessly in their isolation, their brilliance extinguished forever. The universe, an astonishing, boundless expanse filled with wonder and mysteries, will have reached the end of its journey. The universe is truly a remarkable place. It is vast beyond comprehension, brimming with beauty and full of untold secrets. It stretches further than we can even begin to imagine, constantly expanding, constantly evolving. But despite its grandeur and complexity, the universe, like all things, had a beginning, and one day it will have an end. While we are fortunate enough to witness it in its prime, filled with light, life, and wonder, we are also aware that this golden age is fleeting. The question of how the universe will ultimately end is a philosophical puzzle that has long captivated human curiosity. There are theories, of course. Some suggest that the universe will slowly fade into an endless cold, growing darker and more desolate until it becomes a frozen expanse. This is the fate known as the Big Freeze. Others argue that the universe may tear itself apart in a violent and dramatic event, a catastrophic unraveling referred to as the Big Rip. And then there's the idea that the universe might one day collapse in on itself in a cataclysmic implosion known as the Big Crunch, before perhaps being reborn in a new form altogether. But whatever the final chapter may hold, one thing is certain: the universe's story will one day come to a close. Nothing in this cosmos lasts forever. The stars that twinkle above us, filling our nights with light and mystery, will eventually burn out. The black holes, those cosmic behemoths, will evaporate over unimaginable timescales. Even the mighty galaxies that we observe today, sprawling across the cosmos in their majesty, will one day vanish. But for now, we are privileged to live in this extraordinary moment, a fleeting instance in the vast timeline of the universe, when it is filled with life, brilliance, and awe. The ultimate fate of the universe remains one of the greatest unsolved mysteries of all time. Will it end in gradual decay, a slow descent into nothingness? Or will it collapse suddenly, tearing apart in a violent cosmic event? We do not yet know. What we do know is that the universe's story, though it will eventually reach its conclusion, is far from over. At the core of many of these questions is the principle of causality, the idea that every effect must have a cause. In our everyday lives, this principle seems so self-evident. A tree grows because a seed was planted. A star shines because nuclear fusion is taking place in its heart. But when we look to the universe itself, its origins, its creation, we are confronted with a profound enigma. What caused the universe to exist in the first place? Some philosophers, theologians, and thinkers believe that the universe must have had a cause, something beyond the realm of the physical world, something transcendent. This idea is often connected to the cosmological argument, which proposes that the universe could not have caused itself. It must have originated from something beyond it, something that exists outside the boundaries of time and space. Yet there are others who argue that perhaps the universe does not need a cause at all. Maybe it is a brute fact, a self-existing entity that simply is. In the same way, we accept certain laws of physics, such as gravity, without ever questioning their origin. Perhaps we should accept the universe as something that does not require explanation. After all, the universe, in all its complexity, exists. But why? Is it merely an accident of cosmic proportions? This debate also brings into focus the distinction between what is contingent and what is necessary. A contingent being is one that could have been different. The Earth, for example, might not have existed at all, or it could have taken an entirely different shape. Stars, planets, galaxies, they are all contingent. They don't necessarily have to exist in the way that they do. Could the universe itself be like this, something that could have failed to exist? Or perhaps in some way its existence was necessary, meaning that it could not have been otherwise. Could it have always been destined to exist, even if we can't fully understand why? This leads us to yet another mind-boggling question. Could the universe have arisen from nothing? This is where science and philosophy collide in the most extraordinary ways. Some scientists propose that, according to the strange and often paradoxical principles of quantum mechanics, the universe might have spontaneously emerged from a state of quantum nothingness. In the bizarre world of quantum physics, particles can appear and disappear seemingly out of nowhere. In this light, it is conceivable that the entire universe could have come into existence in much the same way, emerging from a void that we can hardly comprehend. So, what caused the universe to exist? How did it begin? The more we search for answers, the more we realize that the questions themselves might be more complex than we can imagine. What we do know, however, is that the universe we know, the one filled with stars, galaxies, and life, is not eternal. Its days are numbered, though they are vast, and we are fortunate to witness its splendor while it still burns brightly. But even as we marvel at the beauty of the cosmos, the ultimate question remains: what comes next?